theoretical elegance meets real-world application. We are immensely proud to share that this prestigious event is partially sponsored by the Tamil Nadu State Council for Science and Technology, TNSCST, under its partial assistance to conference scheme and Academia for Advanced Research in Mathematics.
Today we gather here not only to exchange ideas, Today we gather here not only to exchange ideas and discoveries, but to celebrate the growing importance of mathematics and statistics in shaping cutting-edge technology, solving global problems, and propelling research to new heights.
Over the course of these 2 days, we will witness a wide range of thought-provoking presentations, keynote speeches from esteemed experts, and dynamic exchanges that highlight the evolving role of mathematics and statistics in addressing real-world challenges.
In addition to being a platform for scholarly discussion, this conference serves as a meaningful convergence of intellect, innovation, and interdisciplinary exploration. May the discussions and deliberations over these 2 days spark new ideas, challenge existing boundaries, and pave the way for future research and innovation.
The online session of IC Camshia 2025 is about to begin. Due to technical issue, our guest, Dr. Prabhat Lianga, is unable to join us for the session.
I now cordially invite Dr. R. Uday Kumar, Senior Professor, Department of Mathematics, Gandhigram Rural Institute, to begin the session. Now I request Dr. M. Arul Perum Jyoti, Assistant Professor, Department of Mathematics, to deliver the introduction of the speaker.
Good morning, everyone. It is my distinct pleasure and honor to introduce our esteemed invited speaker for today's session, Dr. R. Uday Kumar, a distinguished senior professor in the Department of Mathematics, School of Sciences at the Gandhigram Rural Institute. With over 25 years of teaching experience and 19 years of active research, Dr. R. Uday Kumar is widely recognized for his expertise in operation research, particularly in inventory management and control, fractal analysis and fuzzy optimization. He has guided over 33 PhD scholars with several others currently under his mentorship. His scholarly contributions are prolific with more than 260 publications. Dr. Uday Kumar's works has attracted significant research funding, having successfully completed 5 major projects with a total outlay of Rs 47.38 lakhs. Beyond his academic excellence, he has delivered 37 invited talks in prestigious national and international forums just in the past 5 years. Among his many honors, he is proud recipient of UGC Mid-Career Award and the Tamil Nadu Scientist Award for Higher Education and Tamil Nadu Senior Scientist Award from Science Society. He also serves as a reviewer for 53 journals, underscoring his influence in shaping contemporary research. Currently serving the Director Academic and the Head of the Department, his leadership and vision continue to inspire both students and faculty. Today we are privileged to hear from Dr. R. Uday Kumar on a topic that promises to be both insightful and impactful. Please join me in welcoming Dr. R. Uday Kumar.
morning. Am I audible? Am I audible? Am I audible, sir? Yeah, 102. Sir, பேசுறது கேக்குதா? Oh. Good morning to all of you. First of all, at the outset, I would like to thank the organizers for giving me an opportunity to express some of the ideas related with fractal analysis and its applications. Anybody heard about the word fractal? Okay, in the lower classes, we have studied about the geometry, the area and the volume, area of the square, rectangle, cube, cuboid, curved surface area, lateral surface area, total surface area, and the volume of the spheres, the cylinder. They are all having definite shape and definite size. So, the father of the geometry is Euclid. Euclidean geometry dealt about objects which are regular in nature. But in day-to-day life, if you have any problem, if you convert into a mathematical model, the shape will be not irregular. So in the year 1985, Mandelbrot introduced the concept fractal. The meaning of the word fractal is a broken, it is a legit word. Am I audible, sir?
Yes, sir.
Yes, sir. Okay. So if you take, and now my doubt is, or my question is, you are occupying a seat. You draw the portion corresponding to the space occupied by you. What will be the area of the space occupied by you? Or whoever may be the slim person or the very bulk person. You are sitting in a chair, you draw the curve or you draw the closed curve, the portion of the space you occupied, whether it will be a rectangle or cube or square, so you find out the area. But you may say that by using integration you can find out the area. But what's the meaning of the word integration? Integration means a summation. But the integral to f of x dx represent area, there will be a curve in between ordinate axis and the x-axis, and between the two ordinates a and b, you have to calculate the area. There the two lines are definite, that is y or two ordinates and x-axis. Only the irregularity is in the curve. There you can find out the area of the space under the curve between the two ordinates and x-axis by using integration, integral a to b f of x dx. Now my question is, you are sitting in a seat or in a chair, you draw the curve of the portion corresponding to the space occupied by you. It will be the closed curve, and what is the area of the space occupied by you? Definitely it will not be a square or a rectangle or cube or cuboid, and you cannot identify the shape of the space occupied by you. So, the fractal analysis or the fractal theory introduced by Mandelbrot comes into the picture. This lecture connects what is the meaning of the word fractal or fractal geometry, where it has got a tremendous applications in various fields. Nowadays, if you develop any subject or if you study any subject, the mathematicians frequently ask the question, what is the use of studying this rigorous mathematics? Whether it has got any real-time application or not. So the first part, what is the definition and everything I will explain. In the later stage, I will explain what is the use of this fractal analysis. And if you have any questions, feel free to ask then and there or at the end of the session. So the outline of my presentation is what is from the fractal history and some examples, and the application. Now just I show some figures and you identify what is he is the father of the fractal theory, Vinayak Mandelbrot. He introduced the concept in the year 1985. Now all the participants or all the delegates are requested to both see these figures and what will you infer by looking at this figure? You can guess. You see this image. You see the next figure. Next. Delegates, can anybody answer what do you infer by looking at all these figures? Any mathematician, please? Am I audible? Hello? Am I audible? I request the delegates, please respond to my questions. I have shown many figures and what is they infer by looking these figures? Okay. If you see all the figures, there is a similarity. In the lower classes, you have studied the similarity between the two triangles. Two triangles are said to be similar if the corresponding sides are proportional and the angles are equal. That is the similarity between the similar son is similar to the father or the mother, or some object is similar to some other object. So there we are comparing the similarity between the two objects.
Excuse me, sir.
Yes,
Sir, your presentation is not visible, sir.
share பண்ணிருக்கேனே.
Okay, sir. Can you check again, sir? Print பண்ணிட்டீங்கன்னா அந்த presentation இருக்கும், sir.
என்ன பண்ணணும்?
Print பண்ணிட்டீங்கன்னா அந்த presentation எங்களுக்கு visible இருக்கும், sir.
ஒரு நேரம் விசிபிள் ஆகலையா?
Yes, sir. Yes, sir. We are trying to tell you, sir.
Okay.
Yeah.
One minute.
Okay, sir. No problem.
Now it is okay, sir?
Yeah, it is okay, sir.
Now it is okay.
So I think we can go to the full screen mode, sir, for presentation.
Full screen mode.
Yeah, full screen mode.
Full screen mode.
Yes, sir. There is a box now, sir. Yeah. Yeah, அவங்க கொடுத்து அமௌண்ட் இருக்கும் அவங்க இப்போ பெஸ்ட் அது ரைட் சார் தெரியுதா
Full screen. Full screen ல தான் கொடுத்திருக்கேன்.
ஓகே அப்போ உடனே ஓகே சார் ஓகே Yeah, you can proceed, sir. No problem, sir.
Okay.
Okay, sir.
Okay. How many delegates are there in this?
Some 50 members are available, sir.
Okay. Then if you give some mic to them and if they answer to my questions, I will be very much encouraged.
Okay, sir. Okay. Yes, sir.
Usually we cannot expect such things in the conference.
Okay, sir. Okay, sir.
Okay.
Yeah, thank you, sir.
And then I request all the delegates, please go through the figures which I show. Please, anybody, the figure எல்லாம் பார்த்து what do you infer? Okay, now it is visible now, sir? Yes, sir. Okay. ஏதாவது ரெஸ்பாண்ட் பண்றாங்களா?
Yes, sir. Yes, sir. They are responding, sir.
Okay. Why is that?
You are already in night, sir.
Okay, now.
Now, answer.
Okay, no problem, but ஸ்லைடு கிளியரா தெரியுதுல்ல?
Clear is clear, sir.
வாய்ஸ் இஸ் கிளியரா இருக்குல்ல?
உங்களுக்கு clear to picture தெரியுது, sir. அதான் sir.
ஆமா, காட்டுது.
Yes, sir, yes, sir. Okay, sir. That's all.
இல்ல, நான் கிளியரா இருக்கா?
Clear ஆ இருக்கு, sir. Nice. Very clear, sir.
வாய்ஸ் கிளியரா இருக்குல்ல?
Voice clear ஆ இருக்குல்ல?
கொஸ்டின் பண்ணலைன்னா பரவாயில்ல, go on talking.
Yes, sir, yes, sir.
Okay.
Thank you, sir. Yeah.
Thank you. So it is, so in the lower classes you have studied the similarity between the two triangles or the two objects. So now triangles are studied. Now the similarity within the object. This is the color cover. So if you take any smaller part, there is a similarity between the smaller part and the larger part. So such a similarity we call it as a self-similarity. Similarity between the two objects you have studied. Today I give the definition of a fractal. The speciality of the subject is this is fractal has no definition at all. That means it has a different types of definition. The first definition I like to give is fractal is an object having self-similarity. What is from the self-similarity? Similarity within the object is called self-similarity. Once again you go through all the images or the figures. If you take any smaller part, it will have the similarity between the whole part. So such a similarity we call it as a self-similarity. So the first definition of the subject of fractal is fractal theory deals about objects which are irregular in nature. What is the first definition? Fractal theory deals about objects which are irregular in nature, because all the regular shapes geometry was discussed by Euclid. So Euclidean geometry you have gone to it. Now we are going to enter into fractal geometry. So the fractal geometry, fractal theory deals about objects which are irregular in nature. The next definition of a fractal is an object having self-similarity. So what is the definition of a fractal? A fractal is generally a rough or fragmented. Fragmented means it has been split into smaller parts. Fragmented geometric shape that can be split into parts, each of which is a reduced size copy of the whole, a property called self-similarity. So the first definition is fractal theory deals about objects which are irregular in nature. Next, second definition is fractal is an object having self-similarity. Now I have shown some real life example for the fractals. Now I gave the mathematical example for fractals. Have you come across the Cantor set? Can anybody say who is the father of set theory? George Cantor is the father of set theory. So Cantor set you might have studied in the undergraduate or postgraduate programs. Now I am going to give the definition of a Cantor set. You take a closed interval 0, 1 or line segment of length 1 unit. Closed interval 0, 1 or line segment length 1 unit. You divide into 3 equal parts. So 0 to 1 is split into 3 equal parts. First part is 0 to 1 by 3. Next part is 1 by 3 to 2 by 3. Next part is 2 by 3 to 1. Now I remove middle open 1/3. That means I remove open interval 1 by 3 to 2 by 3. I remove 1 by 3 to 2 by 3 open interval. So initially I had a line segment of length 1 unit. That line segment I call it as a set capital A0. Next I have, after removing middle open 1/3, I have 2 line segments of length 1 by 3 unit. First length is 1 unit. Now I have 2 line segments of length 1 by 3 unit. That is left side 0 to 1 by 3 again closed interval. Right side again closed interval 2 by 3 to 1. Union of these two, I call it as capital A1. Just you have to imagine, you have 2 line segments of length 1 by 3 units. Left one is 1 segment and the right one is another segment. Union of these two, I take it as capital A1. Again, I apply the same procedure, divide into 3 equal parts and remove the middle open 1/3. So the left side is 0 to 1/3. If you divide into 3 equal parts, 0 to 1/9 and then 1/9 to 2/9, I have to remove it. 2/9 to 3/9, that is 1/3. So I have now 4 line segments. Union of all these 4 line segments, I call it as A2. First set is capital A. Second set is union of 2 line segments, capital A1. And next 4 line segments union, capital A2. Next 8 line segments. Each and every time I take the interval and divide into 3 equal parts. When I remove the middle open 1/3. If you go on doing the process, first set is A0, second one is A1. Finally, the intersection of all these sets, I call it as a Cantor set. I think now you have understood what is meant by Cantor set. Union of, finally, the intersection of all these sets, I call it as a Cantor set. What is the speciality of the Cantor set? Cantor set is a mathematical example for practice. Cantor set is a mathematical example for. Initially, I have shown some figures in the real life. That is the example for practice. What you have inferred, it is all the figures possesses self-similarity. Now I have shown some example, it is a mathematical example for practice. So just I mentioned few properties of the Cantor set. First example is Cantor set contains 2 power k intervals, the length is 3 power minus k. It satisfies the open set condition. Cantor set is the perfect set. In analysis, when a set will be called perfect, it is closed and it ends. So, the Cantor set is a perfect set. Cantor set contains countable set of points. Ultimately, Cantor set dimension is 0.6309. Now, my question is, so far you have come across objects which are having integer dimension. Suppose if you take the board, it is of dimension 2. If you take our space, it is of dimension 3. Dimension 2 means x-axis, y-axis. So if you take the blackboard, that axis and y-axis, it is of dimension 2. If you take the space, x-axis, y-axis, z-axis, it is of dimension 3. Can you give an example of the object? 1 dimension you know, 2 dimension you know, 2 dimension, board is an example, 3 dimension our space is an example. Now my question is, can you give an example of an object having quarter dimension, half dimension, 0.7 dimension? So the next definition of a fractal is an object having non-integer dimension. Fractal is an object not having non-integer dimension. Now, Cantor set is a mathematical example for a fractal. Its dimension is 0.6309. Cantor set contains no interval. Cantor set is closed and non-empty. Next, I give another mathematical example for fractal. You take an equilateral triangle. When a triangle will be called equilateral, all the sides are equal and all angles are substituted. Now, you take midpoints of all the sides. Midpoints of the sides. And you join it. I think you will get a triangle right-sided in the P. Now, you have 4 triangles. Right-sided is 1 triangle. Remove right-sided triangle. Remove right-sided triangle. Now I will continue the process. What is the process? Take the midpoints of the triangle and join it remove the center or the mid or center portion of the triangle. So in each and every triangle, first initially yellow orange shaded triangle, we have taken the midpoints, we have joined it, we get another triangle, it is right sided, it is removed. So we have after removing the right sided triangle, we have three triangles. In all the three triangles, you take the midpoint and join it. So remove the right sided triangle. You continue the process infinite number of times. This is called a Sierpinski triangle. You have to continue infinite number of times. It is a mathematical example for fractal. What is the first definition of a fractal? Fractal geometry deals about objects which are irregular in nature. What is the second definition of a fractal? Fractal is an object having self-similarity. What is the third definition of a fractal? Fractal is an object having non-integer dimension. What is the dimension of the Cantor set? Because Cantor set is a mathematical example for fractal, its dimension is 0.6389. Now the dimension of the Sierpinski triangle is 1.585. Now at this juncture, you have to raise the question. Why? How we get non-integer dimension? That means you have to answer to the question, what is the dimension? Dimension of the whole you have mentioned 2, dimension of the space you have mentioned 3. You said that, I assume that you said that. I assume that the whole dimension of the whole is 2, that means x-axis, y-axis, or if you have to take any point, it will be represented by 2 coordinates. If you take any point in the space, it will be coordinated by 3 coordinates x, y, z, or you have x-axis, y-axis, z-axis. Each and everything is perpendicular to each other. Or in other words, I can define a general definition. If you take it in a linear space or a vector space, the dimension is nothing but number of elements in the basis. When a set will be called when a set in a linear space or a vector space will be called basis, it is linearly independent and span. When a set will be called linearly independent, if we have V1 with a Vn set of vectors or the elements from the vector space, then correspondingly if you are able to find out the scalars alpha 1, alpha 2 up to alpha n such that alpha 1 into V1 plus alpha 2 into V2 plus up to alpha n Vn equal to 0 implies all the scalars are 0. That means all the scalars are 0 means there is not at all any relationship between V1, V2, Vn. If one element is not expressible in terms of other element, such a set we call it as independent. When a set will be called independent, there is not at all any relationship between them. That means one element cannot be expressed in terms of linear combination of other elements. The better example is 1, 0, 0, 0, 1, 0, 2, 0, 1 in half power 3. This linear set contains these 3 elements is linearly independent because you cannot express 1, 0, 0 in terms of or the linear combination of 0, 1, 0 or 0, 0. Similarly, if you take 0, 0, 1, 0, you cannot write 0, 1 in terms of linear combination of other 2. They are not at all any relations. Or if you take any 5, 7, 4, 5, 7 r power 3 can be written 4 into 1, 0, 0 plus 5 into 0, 1, 0 plus 7 into 0, 0, 1. That means I am able to write 4, 5, 7 in terms of the elements 1, 0, 0, 0, 1, 0, 0, 0, 1. If you are not able to find out any relationship between the vectors in the set or the elements in the set, such a set we call it as linearly independent. And if also it spans, when a set will equal to span. Any element in the space will be written in terms of this set, that is 1 0 0 0 1 0 0 0 1. Such a set we will call it as span. If the set is both linearly and independent and span, we call it as a basis, and the number of elements in the basis is called the dimension. Now, here I say that the Sierpinski triangle is a mathematical example of a fractal and its dimension is 1.585. So at this juncture, your doubt arises where this fellow got the non-integer dimension. That means what to give the fraction of the fractal dimension. So according to the fractal dimension definition, the dimension of the Sierpinski triangle is 1.585. So I will later give the mathematical definition of a fractal dimension. Next, I give another example for mathematical example for fractal. You take a closed interval 0, 1 or line segment of length 1 unit. Am I audible, sir? Am I audible? Yes, sir. Yes. The slide is visible? Yes, sir. Okay. So you take a closed line segment of length 1 unit. You divide it, as I said earlier for that set, you divide into 3 equal parts and you are going to remove middle, open, 1/3. But I will get only one portion, but I will paste it in the order to form a triangle. You see the second figure? One portion only I have removed. That is shared in the line segment itself. That means that is removed. The same portion is pasted 2 times in such a way that in order to form a triangle. So totally in the first step, how many line segments I have? 1 by 3, 1 by 3, 1 by 3, 1 by 3. 4 line segments in the line, in the bottom 2 line segments. 1 by 3 unit. In the triangle portion, upper portion, 2 line segments, that is 1 by 3, 1 by 3, totally 4 1 by 3. Now I am going to continue this process infinite number of times. That means what? Each and every line segment divide into 3 equal parts, remove middle, open 1/3 and paste it 2 times. In the first step I have 4 line segments. Even each and every line segment, remove middle, open 1/3, paste it to such that form a triangle. In the triangle portion, you see the second steps. The 3 steps. This is n number of steps. So, this is called the Coach-Snow plant. Coach step. This is the mathematical example for plant. Mathematical example for fractal. And you can enjoy, if you are able to do, you enjoy in the sense, we have just started from a line segment of length 1 unit only. It is a line segment, so you can discuss about properties of the line segment in Euclidean terms. But by the length of the line segment of length 1 unit, after some process, you look at this. You see this? This is a closed curve. It is closed in the square. But if you see the original figure, can you say that it is the shape of a square or rectangle with cuboid cylinder? Now how to find out the area of this figure? Area in the sense, exact area. How to find out the area? By drawing smaller circles or by smaller squares, you can cover the entire portion. But covering by squares, you should not cover extra, or you should not leave any portion which is uncovered. Is it possible? to find out the exact area of this figure. Certainly not possible. So this is an example for fractal object. But this is called a Kochkar. This is Kochkar has infinite length. What is the dimension? That means fractal dimension. It is 1.26. This Kochkar is a continuous curve. When we will call the curve is continuous, if you are able to draw the curve without breaking it, it is called a continuous curve. Or if you will in mathematics, what is the definition of a continuous function? One matrix space to another. If is a function from one matrix space to another function, other matrix space, then we first we have to define continuous at the point, and if the function is continuous at each and every point, then it is called continuous on the whole space. What is the definition of a continuous at a point? M1, D1 is one matrix space domain. M2, D2 is another matrix space, it is a domain. F is a function from M1 to F2. What is the definition of a function at continuous at a point? Given epsilon greater than 0, where x is delta greater than 0, such that P1 of x comma y less than delta implies P2 of f of x comma f of y is less than epsilon. Am I correct? Okay. This is mathematical definition, but practically or geometrically, if you are able to draw a curve without taking your hand, if you are able to draw the curve continuously, the curve is continuous. The curve is continuous, Kochkar is continuous everywhere. But a differentiable know that. When your function is said to be differentiable, limit h tends to 0, f of x plus h minus f of x will exists. Exists means it is a finite. Such curve is differentiable. But this curve is not a differentiable nowhere, anywhere. Kochkar is a continuous. I think we have studied in the postgraduate classes, f of x is equal to mod x is a continuous curve, and it is not a differentiable if x is equal to 0. Similarly, this Kochkar is a continuous curve, but differentiable nowhere. So far what we have seen, the definition of a fractal. What is the first definition of a fractal? Fractal geometry deals about objects which are irregular in nature. What is the second definition? What? Fractal theory, fractal is an object having self-similarity. What is the last definition? Fractal is an object having non-integer dimensions. But one definition is fractal is an object. There are different types of similarity, self-similarity. What is the self-similarity? Similarity between the objects. Similarity between two objects is different. Similarity within the object we call it as a self-similarity. So there are different types of self-similarity. First one is exact self-similarity. Exact self-similarity means it is the strongest type. That means similarity within the object means if you take the smaller part and if you study the behavior of the smaller part, it will both the smaller part and the major part, the whole part, will have the same structure, same size, same properties. So such a similarity, a very strong similarity between the smaller portion and suppose if I want to diagnose whether the patient is having blood, so the sugar or the hemoglobin or whatever may be the test, we take a sample of the blood. What the result of that is, so if the person is affected of diabetic mellitus type 1 or type 2, or suppose in the morning break after before taking birth, fasting sugar is 170, we say that the patient is a diabetic patient. From the small sample of blood, it gives whatever may be the result taken for the small sample is also same as the result for whole sample. So will not take all the blood from the whole body. So if we take the smaller part and we study the properties of the smaller part, and the result is the same for the whole major part, it is a exact self-similarity. Exact self-similarity. Next one is quasi-self-similarity. That means this is loose. The first one is strong, second one is loose. That means so fractal appears approximately but not exactly identical at a different scale. If you change the scale, so the similarity slightly will be changed. Such a similarity we call it as self-similarity, quasi-self-similarity. Exact self-similarity means it is the strongest similarity. Am I audible, sir? Yes, sir. Okay. Next one is statistical self-similarity. First one is the strongest, next one is the loose, this is the weakest. That means this is the best example is random fractals. Neither exactly nor quasi-self-similar. By using all the different types of similarity, we can generate more fractals. One is exact escape type fractals. Next time we are going to see how to characterize or how to identify the object is having fractal nature or not. So the fractality, whether the object is fractal or not, we can study in the characteristics. The characteristics will be specified by iterated function system. So what is the definition of a iterated function system? Finite families of mappings, we call it as iterated function system. Finite families of contraction mappings. Then a mapping will be called contraction from one metric space to another. And you know the pretty well that in a complete metric space the contraction mapping possesses a unit fixed point. So what is the definition of contraction mapping on a metric space from one metric space to another? D of f(x), f of y less than or equal to sometimes means k times d of x comma y, the k varies from 0 to 1. You know the meaning of the word contraction mapping. Contraction mapping on a complete metric space possesses unit fixed. Everything is studied the process. Finite family of contraction matrix, we call it as iterated function system. So by using this iterated function system, I can describe, I can exhibit, I can illustrate, I can explain you. You take a Cantor set, how we have generated Cantor set or how we have created a Cantor set. We have taken a closed interval of length 1 unit divided into 3 equal parts. Middle one, we have removed it. First set A0, second set 2 sets, 2 line segments union A2. Next one is 4 line segments union, 8 line segments unions. Finally, intersection of all these sets, I call it as a Cantor set. Because I have divided into 3 equal parts, it is called a middle third Cantor set. Or you can. So there are different types of Cantor set also. But Cantor set is a mathematical example for fractal. How to describe that map Cantor set by using iterated function system. Usually we follow the here I use the symbol capital X1, capital X2. Capital X1 is a function from real line to real line. Capital S2 is also function from real number to real number, R to R. So both S1 and S2 are having the domain and the codomain as the real line. S1 of X, X by 3. S3 S1 of 1, 1 by 3. S1 of 1 by 4, 1 by 4 divided by 3. Second one, S2 of X is equal to X3 by 3, X by 3 plus 2 by 3. But S1 is a continuous function. S2 is also continuous. Both X2 is one set. Capital S2. Capital S1 is a contraction matrix. You can verify by applying the definition of a contraction matrix. S1 of X equal to X by 3 is a contraction mapping from R to R. Similarly, S2 of X is equal to X by 3 plus 2 by 3 is also a contraction mapping from R to R. So now I have a finite family that is S1 comma X2. Now you are requested to find out S1 of F. What is your F? Middle pair Cantor set. You take any element in Cantor set, find out S1 of that element. You take another element. Similarly, you take all the elements from F, find out the image under S1, you will get some set. Similarly, you find out S2 of F. That means all in F are taken into account, apply S2. S1 of whole set F, S2 of whole set F, together will give F. So F is a Cantor set. So F is a Cantor set, it is a fractal set, it will be described by two finite family of contraction matrices. So this is both S1 and S2 are finite family of contractions. So it is an iterated. But simply enjoy how your fractal is able to express by using iterated function system. I have given the definition of dimension. Now there are different types of definition. One is topological dimension. Euclidean dimension, you know. Topological dimension of a set is always an integer, and when it is a zero, it is totally disconnected. Topological dimension is 1 if each point has arbitrarily small neighborhood with the boundary dimension 0 or so. Next, I define what is called by Hausdorff measure. You take any subset of R power n and S is a non-negative integer. Now I define the stress of delta of Q, that is infimum of sigma equal to 1 to infinity t, diameter of Ui power delta, where Ui is a delta power of Q. You take any set covered by small squares or rectangle, diameter is delta. What is the diameter of your set in vector space? You take any 2 points, find out the d of x comma y, maximum of d of x comma y is a diameter. In circle, twice the radius is a diameter. But if you take any subset of a vector space, maximum distance is the diameter. Now here the delta cover. So delta is a diameter. Now if your delta decreases, limit the delta tends to 0, success of delta you call it as Hausdorff measure. So this is, we will see that in the later stage I will give the definition of your fractal dimension. Euclidean dimension, you know, Topological dimension, you know. Now I give the definition of a fractal dimension. What is the fractal dimension? You take any metric space. You know the definition of the metric space. You set it together with your metric. We call it as a metric space. When a function is called a metric, you know the conditions. You have x comma y, D is a function from x cross x satisfying the conditions d of x comma y greater than or equal to 0 and d of x comma y equal to 0 if and only if x comma y and d of x comma y equal to d of y comma x and d of x comma y is plus comma equal to d of x comma y plus d of y comma z which is called a triangle inequality. Now I give the definition of a fractal dimension. You take any vector space. You take collection of non-empty compact subsets. When a set will be called compact, if every open cover is a finite subset. So if you take any compact subset, A, capital N of A comma epsilon denote smallest number of closed balls of radius epsilon greater than 0. N of A comma epsilon denote smallest number of closed balls of radius epsilon greater than 0. Limit epsilon tends to 0, logarithm N of A comma epsilon, here the logarithm is with respect to the base g, divided by log 1 by epsilon exists, then B is called the fractal dimension. So the fractal dimension definition you are given, so it is a non-integer dimension. To find out the dimension of a fractal object, we have Hausdorff dimension, box counting dimension, similarity dimension, correlation dimension, different types of dimension rather. Each and every dimension is suitable for certain fractal objects. That we have to identify which dimension is suitable for this fractal object. Now I give the definition of box counting dimension. We take any non-empty bounded set, n of delta comma f in smallest number of sets of diameter at most delta. Now I give the definition of lower and upper box counting and dimension. Lower is limit infinity delta tends to 0. Log n of delta f by minus log delta. Next, upper box counting dimension. Diameter dimension of upper dimension is limit supreme of delta tends to 0. Log n delta upper epsilon. If these two are equal, then we call it as box counting dimension. The next definition is similarity dimension. Now I am going to enter into the application form. Are we audible, sir? Yes, sir. So far what we have seen is what is called by fractal, what are all the different types of definitions, what is the real life examples for fractal, mathematical example for fractal. Now I am going to give the applications of fractal theory, especially in the medical field. Medical image processing, image compression, signal processing, time series analysis, mathematical modeling of dynamical source. Anybody knows about the disease called epileptic seizure? Epileptic seizure is a disease called okay, could you repeat? Epileptic seizure, Tata will put there. Yes. Attentive, they all listen. only? Then எப்போ முடிக்கணும்?
Actually, it was scheduled 10:15, sir.
Okay.
Yeah.
Okay. Okay.
Yeah.
ஒரு 10 minutes முடிச்சேன்.
Okay. Okay.
Oh, okay. Next speaker is also ready. Am I correct?
Yes, sir. It is ready, sir.
Oh. Epileptic season. The kaka valipu. Suppose if the person is affected with epileptic seizure, without knowing the symptoms, he will fall down. Kaka valipu வந்துச்சுன்னா கீழே விழுந்துடுவார். அது வர்றதுக்கு முன்னாடியே அவனுக்கு தெரியாது. கீழே விழுந்துட்டு எதிர்ச்சதுனாலையும் the speciality of this disease is முன்னாடியும் சிம்டம் தெரியாது, எழுந்த முன்னாடி தெரியாது. எவ்வளவு நேரம் விழுந்திருப்பார்? 1.98 seconds according to medical record. 1.98 second. விழுவதற்கு முன்னாடி வருது. There are numerous number of neurons are. யாருக்காவது தெரியுமா பிரெயின்ல எப்போ நியூரான்ஸ் இருக்குது? இப்போ இது புதியமான பேரை நியூரான்ஸ் ஆனா பார்த்தாலே போகும், பேரை கேட்டாலே போகும், அது இல்லைன்னு சொல்றோம்ல. ஏன்னா அவங்கள பத்தி ஏற்கனவே அது ஒண்ணு சண்டை போட்டுருவோம். அப்ப நியூரான் திடீர்னு சண்டை போட்டோம்னு அங்க வந்து வந்து கொலையில
Sir, I mean, the presentation is not visible, sir.
presentation is not
Yeah,
received.
now it is, now it is.
Okay, yeah?
Yes, sir. It is, yes, sir. It is okay, sir.
Oh. Now it is okay completely. Okay, sir?
Yes, sir.
Okay. So human brain, the neurons move, the period, ஒரு fever, ஒரு stomach pain, heart attack, எல்லாமே symptoms தெரியும். அப்ப போய் நீங்க எப்படி heart problemனா we will go to the cardiologist. Cardiologist will ask the patient to undergo a. If the brain is affected, if you go to a neurologist, they will ask you to undergo electroencephalogram. Electroencephalogram, EEG signal. Heart rate ECG signals. நான் இங்க காமிச்சிருக்க ஃபிகர் வந்து electroencephalogram signals. Human brain உங்க மூளையில வந்து உங்க தலையில ஒரு 24 electrodes or at least 9 electrodes will be attached. ECG க்கு வைக்கிற மாதிரி. அந்த electrodes வச்ச பின்னாடி நமக்கு ரீடிங் எடுத்தோம்னா ECG பார்த்துருக்கீங்க. இங்க காமிச்சிருக்கிறது EEG, electroencephalogram. இது வந்து இங்க ஒரு கருவு பார்த்துருக்கீங்க. It is not a sine curve or cos, log, sin x, log x equals. This is a continuous curve over a differential. ஆனா இதுக்கு ஈக்குவேஷன் கிடையாது. ஹியூமன் பிரெயின் திடீர்னு சடனா இந்த மாதிரி ஷாக் ஏற்படுறதுனால இந்த எலக்ட்ரோஎன்செஃபலோகிராம் ரீடிங்ல நம்ம என்ன சொல்ல வரோம் அப்படின்னு கேட்டீங்கன்னா இதை ஸ்டடி பண்ணி we have collected this data. Our scholar has gone to Brain Research Center at Haryana. Haryana Brain Research Center. There the medical doctors are doing research. Why I say medical doctors? Doctor, we are not doctors. The medical doctors are doing research in the human brain. Available the data. இதுக்கு ஒரு மேத்தமேட்டிக்கல் எக்ஸ்பிரஷன் எழுத முடியுமா அப்படின்னா கால் எக்ஸ்பிரஸ் கொண்டு ஒரு லெஃப்ட் ஹேண்ட் சைடு எழுதிருக்கேன் பாருங்க ஒரு எக்ஸ்பிரஷன். சரி, அந்த மேத்தமேட்டிக்கல் எக்ஸ்பிரஷன் you read it. Now what I want to convey is I find out the fractal dimension. Right side எழுதிருக்கோம். Fractal dimension is 1.5. Fractal dimension is 1.3. Normal patientக்கு ஒரு fractal dimension value. அதை விட இது கூட இருந்தது அல்லது கம்மியா இருந்தது அப்படின்னா the person is affected. affected by epileptic seizure. Person is affected by. So, நான் தான் டாக்டர்னு நான் சொல்றேன். We help the neurologist to diagnose, to predict whether the patient is affected by epileptic seizure. காக்கா வலிப்பு வந்திருக்கா வரலையாங்கிறதுக்கு நார்மல் பேஷண்ட்டுக்கு ஒரு ஃப்ராக்டல் டைமென்ஷன் இருக்கு. அப்நார்மல் irregularity இருக்கிற epileptic seizure பேஷண்ட்டுக்கு ஒரு ஃப்ராக்டல் டைமென்ஷன். By based on the fractal dimension, this is another tool. எப்படி ஒரு டாக்டர் வந்து ஒரு டிசீஸ் எப்படி டயக்னைஸ் பண்றாரு? சிம்டம்ஸ் ஒன்று, யூரின் டெஸ்ட், மோஷன் டெஸ்ட், பிளட் டெஸ்ட், அதுக்கப்புறம் இசிஜி, டிசீஸுக்கு தகுந்த மாதிரி ஸ்கேன்ல கிளியரா தெரியலையா, சிடி ஸ்கேன் கிளியரா தெரியலையா, பெட் ஸ்கேன். ஸோ எல்லாமே ஒவ்வொரு ஸ்டேஜ் என்னன்னா பரம்பரை அக்யூரேட்டா டிசீஸை டயக்னைஸ் பண்றது தான். அதே மாதிரி நம்ம மேத்தமேட்டிக்ஸ் என்ன சொல்றோம்னா, பர்டிகுலர்லி ஃப்ராக்டல் என்ன சொல்றோம்னா, இந்த மாதிரி irregular curve கொடுத்தீங்கன்னா we will find out the fractal dimension. அந்த fractal dimension பேஸ் பண்ணி அவருக்கு epileptic seizure காக்காவலிப்பு இருக்கா இல்லையா. அதுல டிஃபரெண்ட் டைப்ஸ் இருக்கு. என்ன டைப்னு சொல்லலாம். இதுல இன்னைக்கு வரைக்கும் உள்ள சேலஞ்ச், what are all the challenges for the doctors? இன்னைக்கு காக்காவலிப்பு வந்துருச்சு. When it will reoccur again, திருப்பி காக்காவலிப்பு எனக்கு காக்காவலிப்பு வரது ஒரு ஆர்டினரி மெடிசைன்ஸ் இருக்கு. மெடிசைன் they have to take lifelong. ஒரு டிரைவர் பஸ் அது ஒரு கிணத்துல போகிறது. கிணத்துல சாதாரணமா அது இருந்தா எந்திரிச்சு அது ஒரு தீரா நடக்கிறது தான். அதுல வந்து எந்த விதமான பாதிப்பும் இல்லை. ஒரு டிரைவரா இருக்கா திடீர்னு வாங்கி வந்துட்டு அப்படிலாம் ரீசெண்டா சில நியூஸ் எல்லாம் கேள்விப்பட்டிருப்பீங்க. சில டிரைவர்ஸ் வந்து வண்டியை ஓரமா நிப்பாட்டுவாங்க. சில டிரைவர் நிப்பாட்ட முடியாம அஃபெக்ட் ஆகி அவரும் போய் இந்த பேசஞ்சர்ஸும் போனதெல்லாம் நீங்க இவ்வளவு come across in the newspapers. whether such news will have it or not, I do not know. Anyhow, the disease will be complicated if you are doing a risk job. Risk job என்னது டிரைவர் இந்த மாதிரி. அப்ப இன்னைக்கு அவருக்கு சீசர் வந்திருக்கு, காக்காவலிப்பு வந்திருக்குன்னா அடுத்து என்னைக்கு வரும்? அப்படி reoccurrence of the seizure so far predicted. அதுபோக இப்ப இது வந்து ஒரு ஃப்ராக்டல் கர்வ், ஃப்ராக்டல் ஆப்ஜெக்ட் மாதிரி ஃப்ராக்டல் கர்வ். ஃப்ராக்டல் கர்வ்னா என்ன? இதுக்கு சைன் கர்வ், காஸ் கர்வ் மாதிரி ஒரு பேட்டர்ன் கிடையாது. ஒவ்வொரு இப்ப நான் அடுத்த இது வந்து நிறைய சாம்பிள்ஸ் எடுத்தது. அதுல மேல டாப்ல ஒரு போர்ஷன் பார்த்துருப்பீங்க, அதுதான் பிரெயின் அஃபெக்ட் ஆன போர்ஷன். ஸோ நீங்க அவர் தூங்கும்போது எடுக்கணும், சீசர் வந்தப்போ எடுக்கணும், சீசர் வர்றதுக்கு 10 நாளைக்கு முன்னாடி, சீசர் வந்து 10 நாளைக்கு, காக்காவலிப்பு வர்றதுக்கு முன்னாடி, காக்காவலிப்பு வர்றதுக்கு பின்னாடி, இப்படி நிறைய டைம்ல எடுத்து பார்த்தீங்கன்னா abnormalities, irregularities you can realize, you can visualize. ஓகே, நீங்க என்ன சொல்ல போறீங்கன்னு என்ன கேட்குறீங்க? நான் we will calculate fractal dimension, epileptic seizure இருக்குன்னு கன்ஃபார்ம் பண்ணுவோம். அதுக்கடுத்து என்னன்னா ஒவ்வொரு கருவுக்கும் fractal dimension கண்டுபிடிச்சு approximate, not exactly, by using time series analysis in the statistics, applying statistical tools, we can approximately predict the reoccurrence of seizure. அடுத்த காக்காவலிப்பு என்னைக்கு வரும்? time now predict பண்ணி இந்த டேஸ்ல எல்லாம் இருக்கும். இது வந்து it will vary from patient to patient also based on the medical history, அவருக்கு other disease complication, அவர் எவ்வளவு டோஸ் எடுத்துக்கிறாரு. There are lot of factors we have to take into account. But if you collect all the data and if you collect the irregularities of the human brain by observing the signals in the human brain by using electroencephalogram signals, if you calculate the fractal dimension and if you apply the statistical tools, we can approximately predict the reoccurrence of the seizure. And another point is, to calculate the fractal dimension definition I have given, but to calculate the fractal dimension, there are, as I said earlier, Box-Combine dimension, Weierstrass dimension, நிறைய இருக்கு. அதில் ஒவ்வொரு dimensionலையும் certain drawbacks are there, and there are lot of methods to calculate the fractal dimension. One method is Gauss-Seidel method, another method is Papillon and Gould sigma method. We have proposed a new algorithm that is called SMR algorithm. Our scholar and myself has proposed a new algorithm that is called the SMR algorithm by overcoming all the shortcomings in the existing literature. Literature இருக்கிற மெத்தட்ஸோட பெஸ்ட்டாக சொல்லியிருக்கோம். அதுக்காக எங்கள் மெத்தட்லாம் பெஸ்ட்டுன்னு சொல்ல வரல. அதுக்கப்புறம் மெத்தட்ஸ் அல்காரிதம்ஸ் நாட் இன்க்ளூட், பட் ஓவர் த drawbacks in the existing literature, we have proposed a new algorithm which is called SMR algorithm, that is to find out the fractal dimension. So by using fractal dimension, we can calculate the reoccurrence of the seizure. And another application is in cancer side, but if the time permits, I will explain, and otherwise I like to conclude my talk, and thank you for your patience hearing. If you like to carry out the research in the field of fractal theory, either in the pure side or in the application side, very well you can contact me through phone or through mail ID, and we have published a good number of research articles in this particular field also. And this is an emerging field, and it has a lot of tremendous application, not only in medical field, in physics. There are big journals also, Physics 8, Chaos, Solitons, Fractals, in a very scientific one journal named Fractals, journal named Fractal Law. So if you have any doubts, feel free to ask now, or after the conference is over, feel free to contact me through phone or mail ID. Thank you for your patience hearing. Thank you for the opportunity given to me. And once again, I thank the organizers of this conference. Thank you.
Thank you very much, sir, for the insightful talk. We truly appreciate your time and effort, especially for joining us on such short notice. Your contribution has greatly enriched today's session.
Hello. Thank you, sir. Thank you. But we are sure we will ask the audience whether they have questions.
If you have any queries, you can ask. Thank you very much, sir, for the insightful talk. We truly appreciate your time and effort, especially for joining us on such short notice. Your contribution has greatly enriched today's session.
Thank you.
Now I request all the participants to go for the tea break in front of the library hall and come back in 10 minutes.
அவன் யாருமா மேக்கப் பண்ணி நிற்கிறது?
Thank you all for joining us again. Now I request Dr. S. Arul Amatharaja, Assistant Professor, Department of Mathematics, to introduce the chief guest.
Good morning, everyone. It gives me immense pleasure to introduce our distinguished speaker of the International Conference on Computational and Applied Mathematics, IC CAMSTIA 2025, Dr. D. Anthony Xavier, former head of the Department of Mathematics at Loyola College, an eminent academician and a researcher in the field of mathematics. He is currently serving as an associate professor in the Department of Mathematics at Loyola College, Chennai. His profound area of interest in research includes graph theory and the theoretical computer sciences, fields that are both foundational and cutting edge in today's computational world. With 25 years of experience and 11 years of research experience, Dr. Xavier has significantly contributed to the academic and research community. He has guided 12 research scholars and is presently guiding 5 more students in their pursuit of knowledge. Dr. Xavier's scholarly contributions are remarkable. He has published 100 research articles in reputed journals, delivered 7 invited talks, and has taken the lead in organizing 12 conferences, fostering collaboration and the exchange of ideas. Adding to his achievements, he is also the author of 10 books, many of which serve as valuable resources for those preparing for competitive examinations. His dedication to the field of mathematics, his commitment to academic excellence, and his inspiring journey are truly commendable. We are honored to have him with us today, and we look forward to gaining insights from his knowledge and experience. Welcome, sir.
I now cordially invite our chief guest, Dr. D. Anthony Xavier, Associate Professor, former Head, Department of Mathematics at Loyola College, Chennai, to deliver the seminar.
Good morning to all of you. First, I thank the organizing committee and head of the department and Dr. Arul for inviting me to this international conference. Actually, I am happy in 2 aspects. The first one is many of my students are research students and PhD students are working here as faculty in this college. I'm happy to see them again. I have seen them as students, and now I'm seeing them as professors and lecturers in different dimensions. I'm very happy to see them. And the next point is my son and daughter both are studying in this college. So I'm very happy to come here, and I thank the management. Okay, so dear students, so my topic is geodetic problems. So geodetic means it is the shortest path, right? Okay, so basically path related problems. So our life is a journey, right? Journey means so journey through paths. Now we have paths like this, right? So the thing is, different paths are there. So how we are selecting the paths, right? So these are all railway tracks, and even in our body system, the neural system itself, we have complicated network, right? Okay, so network in the sense, actually suppose some person X is undergoing some critical operation, means how the robot is identifying, means the robot will fix the path, right? Okay, so fix the path to the particular organ traveling towards. So that means so it is so there the concept of path is working here, right? Within our body, and in social network, right? So the routing concept, so the path concept, yeah. So path related problems. So these are the famous problems. Shortest path problem, as the engineering students and arts and science students, you could have studied this in graph theory, shortest path problem. That registers algorithm, so it is the base for the shortest path problem. Other algorithms are there. Then the Hamiltonian problem, that is the traveling salesman problem, and Eulerian problem based on postman problem, right? Okay. And this fourth category is the Wiener index related problems. So it is chemical structures. Okay. So these are all the problems dealing with paths, right? Okay. So when we are studying some topic means or doing research in topic means so what are the applications? So that's the first question. Okay. So if it is applied in various aspects means we can start on research, right? Okay. So my topic is geodetic, so that means so these are the justifications actually how the path related problems are applied in various fields, like say in the first routing networks, so that is internet, road maps, and etc. Then logistics and supply chain optimization. So in this management side, between the companies, how the transportation and other things, within the shortest route and within the minimum cost, so the path related problems plays a role, and scheduling and planning, that is flight timings, right? Okay. Bioinformatics, that's what within our human body, right? DNA sequencing analysis, even in our neurosystem, so the path related concepts are used, and social network analysis, how clustering concept, suppose what is the trend today, right? So finding also which area, that means through which routing, which path, so the clustering happens, okay? So that kind of concepts. Then robotics warfare, then automatic traffic light management, so based on the traffic, so in particular path, so we have to arrange the signal system, Instagram, filter suggestions, so Google Maps, recommendation engine, that is path frequency analysis, security and control systems, okay? Then traffic and navigation systems, so cognitive science and neural networks, military strategy and surveillance, smart city planning, finally smart city planning, okay? So these are all actually application side of path problems. So various applications are there. So we can start now. So the path problems. Actually, so the geodetic problem is a graph theoretically based problem. So theoretical aspects are there. I can explain. So suppose within a graph means so what the geodetic problem means, so you can take some 2 points means, so within the 2 points, so you can cover all the possible shortest distance between the 2 points, right? Okay. Then the question is there, how many that kind of points are required to cover the entire graph vertices? Okay. Now I can give an example. So just consider this famous theta graph, right? Okay, so here are some 5 vertices are there. Okay, so the question is, you have to take, suppose you are taking 2 points means, so, B means, so actually you can cover all the shortest points between the 2 vertices. So it is actually, this, the first branch is covered and second one is covered, third, everything is covered, right? Okay, so the whole graph is covered, right? So these 2 points are enough to cover the whole vertices. So suppose I am extending this graph, something like this. Okay. Okay, now how many points are required to cover the entire graph? So these 2 points means so only we can consider the shortest path between them, right? Okay, so these 2 points will cover all these shortest paths, right? But here the paths are there, no, so not covered. So we can get one more vertex, right? Okay, so by taking this and this, no, so here this is the shortest path, no. So here we can go, and here again 1, 2, 3, 4, 5. Yeah, all the length 5 only, okay. So this path is covered, and again this path is covered, and again this path is also covered, right? Okay. So, so here the geodetic set is actually, minimum geodetic set is A, B, C, right? Okay. So minimum geodetic set is this. Okay. So this is a very old problem, and Harari, so he introduced this problem. So many results have been derived, and this geodetic problem is also NP-complete problem. Even though this looks like a simple problem, it's basically for general graph it is a non-polynomial complete problem. Okay. Now our problem is slightly different. So how our problem differs? Actually, this is our Loyola College, and suppose if we consider this college as graph, so we get this. Okay. So the question is this. So here we have to arrange the security persons, in different places, okay, so security persons in different places, such that each pair of security can guard only the building's lines on the unique path, okay, so unique path. So there the unique means, so we are covering all possible shortest paths, right, okay. So here 2 points we are taking, 2 securities are taking this, the 2 securities will take care of only one path, okay. So if you consider this graph, actually the old geodetic problem is we can cover all the paths, right? Okay, we can cover all the paths. But in this strong geodetic, actually recently some 3-4 years back, Dr. Paul Manuel and Sandy Clever and my research group introduced this problem. Many works are going on because of the uniqueness of the problem. The thing is, so if you consider these two points means it can cover only one path, right? Okay, it can cover either one of the paths, right? So then to cover other paths, we require more points. Okay, so that's what we are saying. Okay, so the security persons has to be placed in such a way that so 2 persons can guard only one path, right? So in that way, how many persons are required to cover the entire college network, right? So that's the question. Okay, so this is actually the answer. 1, 2, 3, 4, 5 persons are required. Okay, yeah. Now the thing is, this is the whole geodetic problem. This is our newly defined geodetic problem by Paul Manuel and the group, right? Okay, so what are the main difference? So the first one is, it is the convexity related problem. Okay, in real analysis we are talking about convex. Convexity means it is closed, any 2 shortest path means within the set itself will become all shortest paths, right? Okay, so that's the convex concept. So the whole geodetic problem is a convexity problem, okay? But this newly defined strong geodetic problem is a combinatorial problem, okay? So combinatorial problem means which path can be selected, right? Okay. So according to our newly defined this strong geodetic problem, how many points are required? For example, you take this graph. With this 2 point, I can cover one of this branch, right? Okay. So for example, I am covering this, right? I am covering this means these 2 points cannot cover this line, right? This path, right? Okay. To cover this, we require some more points somewhere here. Even you can take this or this, right? Now these 2 points can cover this path and this can cover this path, right? Similarly, to now this point and this point cannot cover any more word is that. And similarly, to cover this branch means definitely you have to take one more, okay? And to cover this we have to take one more, right? To cover this we have to take one more, right? And now come here, this pair can cover only one, and this pair cannot cover this because what are the distance? Is it the shortest path? 1, 2, 3, 4, 5, 6, 7. Yeah, it's shortest path only. Okay. So this pair can cover one more, right? And the only thing is here it is left out. We have to take one more, right? Okay. So this many points are required. So this is the basic difference between the geodetic problem and the strong geodetic problems. Okay. So geodetic problem has its own application, but this strong geodetic problem is slightly stronger in nature, right? Because so in even our railway network means we cannot categorize under geodetic problem. Okay, so geodetic means all suppose you are taking 2 cities like Chennai and Delhi means according to geodetic problem between Chennai and Delhi all possible tracks are covered, right? Okay, but according to this strong geodetic problem, even you take Chennai and Delhi means one track will be covered, right? Okay, with some 2 two offices, and suppose you are taking one more track between Chennai and Delhi means we require some more offices to cover, right? Okay, so it is actually in security base or in terms of logistic, everything, right? Logistic or communication, everything, it is easy if you consider the concept of strong geodetic. Okay, so for the nature of strong geodetic, so this is highly preferable than geodetic problems. And one more thing, so we have a lot of research scope because comparing to convexity concept, so the combination combinatorial concept is it's highly challenging in terms of research. Okay. Yeah. So this is actually the geodetic, strong geodetic concept. So my students worked in this concepts. Okay, so this is another example regarding a road map. Yeah, so these are all some bounds. Like the first bound is from the isometric path problem. Actually, what do you mean by isometric path means? Suppose we are given a graph. How many shortest paths are required? How many shortest paths are required? The number of shortest paths to cover all vertices in that graph. Okay, so that is called the isometric path problem. It is actually this again a combinatorial problem, like minimum number of collections we have to consider. Okay, so here we are connecting the strong geodetic and isometric path problem, and this is the lower bound and the upper bound. Lower bound and upper bound, everything is given in terms of isometric path problem. Okay, so the concept is very simple. Suppose here we are taking strong geodetic sector, the coordinate is S, and within the coordinate, suppose we are taking S segments, so how many paths are possible? Suppose we are having n vertices, I mean, or we can take some m vertices means, in this geodetic set means, so how many paths are possible? Different paths are possible between two vertices. How many paths are possible? Two vertices, one path. Okay. So how many vertices? How many paths are possible? NC2 paths. Yes or no? NC2 paths. Okay. So two vertices, one path. Sorry, NC2. Okay. NC2 paths are possible. Okay. So NC2 paths are possible, and MC2 paths cover all vertices, and IP, that isometric path means it is a minimum number. So minimum number means we have this inequality. We have this inequality in the sense, so if you expand, you will be getting some quadratic equation. From the quadratic equation, you will be getting this lower bound. Okay. Simple idea. And upper bound is obvious. Okay. Strong geodetic problem means strong geodetic problem, the number of points, and isometric path problem means it is in terms of number of paths. Okay, number of paths. So each path is having end vertex and the starting vertex. Okay, so each path is connected by starting vertex and end vertex. So each path is equal to 2 points. Each path is equal to 2 points. So IP of G means that much number of paths into 2 points means it will cover all vertices. Okay, so strong geodetic of graph is less than or equal to this one. So the upper bound, right? Okay, so we are able to give the strong geodetic problem number in terms of IP, that is isometric path problem, lower bound and upper bound. The next term we are talking about the complexity. So why we have to take consider complexity means, suppose as a researcher you should know you are dealing with some problem means, basically it should be NP complete problem. Okay, NP complete problem. Then only we have some challenge to find to proceed with that problem. So I can give you the reason. See, for example, if you consider a tree means, what is the geodetic problem for this tree? Suppose you are considering tree means binary tree or any tree. So the geodetic problem, if you consider this over this end vertex, it is going to be the number of leaves. That is enough, right? Okay. So here NP complete. So I think you are familiar with this concept NP complete. Three things are there: polynomial time problem and non-polynomial time NP complete. Then NP hard problems are also there. Okay. So once you prove the given problem is NP complete, then it is a challenging problem. It becomes challenging problem, right? Okay. Say for example, domination problem is NP complete problem for general graph, right? So we can work on this. Suppose you are taking domination problem for a line graph, it is not a challenging problem. Okay. So actually in this type of problems, what the question is, say for example, you are taking domination problem means, suppose you are given a graph with n vertices, some k is given, Now, is it possible to find a domination set, with the order less than or equal to k in this graph? Okay, so this is the question, right? We call it as inference, right? See, understand the question. Suppose graph is given with n vertices, okay? Graph is given as n vertices, k is given. Basically, k is less than or equal to n, right? Okay, k is less than or equal to n. The question is, given, suppose you are talking about domination problem means, k is given. For this given k, is it possible to find, whether there exists a domination set with the ordinality less than or equal to k? So that is the question. See, for example, you are given some graph with 1 lakh vertices, okay? You are talking about our Chennai city means, each house you are taking a vertex means, it come around some crore, 1 crore vertices, right? Okay, you are connecting by graph. Suppose you want to fix the street lamps in each street. Street lamp concept is a domination concept. Street lamp, you are fixing street lamp means, it can cover the neighboring vertices, not only covering neighboring vertices, the distance to vertices also. Okay, so we can bring that under the domination problem, fixing street lamp, right? Okay, the question is, suppose you are given some 1,000 street lamps, okay, 1,000 street lamps. So the question is whether within the domination concept, the 1,000 street lamps can be fixed with 1 crore vertices. Okay, so that is the question. So this type of question, so we are considering in graph theory. Okay. So the same question, you are asked in the path. Okay, so in the path, suppose path is having some 1,000. About this 1 crore vertices, so path is having 1 crore vertices. So actually, what is the domination number for the path?
1.
N divided by
Nomination.
number.
N by 3.
N by 3. Roof, I think roof no. Okay, n by 3. Okay. Yeah, plus 1 or n by 3 vertices. Okay. So here the answer is very easy. The thing is 1 crore vertices are there means approximately we require 33 lakhs something we require, okay, to dominate. But suppose you are given k is equal to 1,000, immediately we can say the answer no. Okay, within 1,000 we cannot find the domination set. Okay, so we consider this type of problem, that is called the problem. Whether the problem is solvable in polynomial time means it is called a polynomial time solvable problem. Okay, suppose it is not solvable in polynomial time means it is called the exponential time problem and it is called the NP complete problem. Okay, other categories are there. NP hard problems, we are not entering into that. NP hard or harder than NP complete problems. Okay, yeah. Similarly, the geodetic set. Suppose the geodetic set is given in terms of tree means, I told you, based on the leaf. If you know the number of leaves, immediately you can say the answer, right? Okay. Suppose you are given a tree with some 1 crore vertices. Suppose there are leaves with some 10,000 leaves. It's not binary tree, maybe any tree, right? Okay. Leaves with some 10,000 leaves, and suppose the k is given over here like some 500. The question is there a geodetic set with cardinality less than or equal to 500 for this tree structure means? Immediately we can say. Okay, so how many leaves are there? 1,000 leaves are there. What is gate given here? 500. Okay, 500. Now the question is, what is the question? The question is there a geodetic set with cardinality less than 500, less than or equal to 500? Okay, immediately we can say no, because these are the geodetic system, minimum geodetic system. Actually, this vertices are called simplicial vertices. Okay, simplicial vertices means the neighborhood vertices. If you collect all the neighborhood vertices, it form a clique, right? It form a complete graph. Okay, so the simplicial vertices are in any geodetic set. We have some results. Based on that result, so this clicks will be there. I think this simplicial vertices. Simplicial vertices will be in any geodetic set. So there are 1000 means actually for this tree structure. This is the answer. 1000 is the geodetic section, right? Okay. So we can give the answer. No, it is not possible. Okay. So this type of question rises. Suppose here we are considering a same question. The question is, suppose you are given random graph with a large number of vertices and given k. The question is whether there exists for that random graph with, for example, some 10 lakh vertices. The question is it, suppose you are given k is equal to some 1000, whether there exists a geodetic set less than 1000 vertices. That is the question. Okay. So whether this question is solvable in polynomial time means no. So that is the answer. Okay. So strong geodetic problem is NP complete. So to prove NP complete, so that is actually a challenging part. Suppose I think many of you are doing research in graph theory. Okay. So and we are taking many networks. So even in our college also, students are taking graph theory. They are doing in terms of network concepts. So in network, finding various graph theory aspects. So it is okay. It is appreciable. The only thing is you can come to this side also. Okay. So this side is called the computational complexity concept. Okay. Computational concept. It is highly challenging, right? Geodetic problem is already NP complete, but that is different. Geodetic problem is already NP complete, but our defined problem, our proposed problem, strong geodetic problem. Again, the question is whether is it NP complete? Okay, so this is the construction. Actually, for geodetic, this NP completeness proving various methods are there, like 3-step method, and this method is called reduction method. Okay, so reduction method makes suppose already we are taking proved NP complete problem one side. The other side, from the given graph, we are constructing some graph. Okay, we are constructing some graph with the help of already defined NP complete problem. We are trying to prove the proposed problem NP complete. Okay, so that concept is called I think polynomial reduction, right? Okay, so it is something like a Drogler bite. In Drogler films, you can see Drogler is there. It bites some person means so that person will change into Dracula, yes or no? So at the same concept. So this is already a Dracula. If you are connecting with this successfully means so this will become Dracula, right? Okay. So that's the concept. So here a lot of rules are there. General graph means it is okay. Suppose you are taking bipartite graph means so that you are constructing the new graph, no, that also should be bipartite. Suppose you are taking some caudal graph means you are constructing some new graph is there, no, so that also should be caudal graph. Okay. So that so many rules are there. So here this is the construction. This is the general graph given. Okay. So here this construction goes like this. No? We are taking that 3 layers are there. The first layer is so we are taking the given graph, right? The second layer say we are taking the same number of vertices in the second layer and we draw one complete graph here. Okay, so complete graph with the same number of vertices of the given graph. Then we are connecting all the corresponding vertices. Okay, and then again your third layer is there. The third layer is containing all independent sets, right? Okay, independent sets. Second one is clicker. Third one is independent sets. Okay, so these are the 3 layers. And here, what is the problem we are taking means? So we are taking dominating problem. Okay, we take dominating problem, and the dominating problem is already NP complete. Okay, so it is available in the literature. So from the dominating problem, we are attacking the strong geodetic problem. Okay, so if you see the nature of the graph, I told you. So these are all simplicial vertices, right? So these are all simplicial vertices means definitely this will be in the geodetic set. Okay, so definitely it will be in the geodetic set. Any geodetic set it contains. Okay, இப்போ இங்கிருந்து நீங்க ஸ்டார்ட் பண்றீங்க. You are starting from here. How the geodetic may go? One possibility is இங்கிருந்து இப்படி போய் Yes or no? Right? So, between this, all this path covers all the vertices of this layer, right? Now this layer is the first layer, okay? So, inga vandu first layer, how we can select the shortest path? Suppose you are starting from here, straight at your mouth, okay? Inga halt avum, or you can go here, you can halt here. Can you go up to this? Can you go up to this? Just imagine. My question is, I am starting from here. I am traveling up to this W. Can I go through U up to Y? Will it be a shortest path? That's the question. No, very good, very good. I can go here W. This is complete graph. No, directly I can go here. I can go here. So this one is not a shortest path. Okay. So suppose I am traveling from this third layer to this first layer, means what are all the possible shortest paths? Okay. Point number 1, I can travel up to this. Point number 2, I can go here, I can move one step in the graph. Okay. So these are the two possibilities, right? So these are the two possibilities in the sense. Now we have to cover the vertices in the graph. Okay. Vertices in the graph means actually இது வந்து geometric set குள்ள இருக்கு, right? இங்க வந்து you no need to take any point in the geometric set because already everything is covered here, right? And to cover the vertices, we have to take some points in this first layer, some point in the first layer. Some point in the first layer means from here I can go up to this, right? I can go up to this. Okay? So I am taking that type of points, right? That type of points. So it will form a geometric set. அப்படியே மைண்ட்ல வச்சுக்கோங்க. So நீங்க அந்த மாதிரி பாயிண்ட்ஸ் எடுக்கணும் இல்லையா? say for example I am taking this point and this point and this point. Okay? இது அப்படியே ஃபில்டர் பண்ணுங்க. You go back. So filter means what? Remove this set. இந்த பாயிண்ட் மட்டும் நீங்க இங்க எடுத்துட்டீங்கன்னா when you are going here, what will it become? Very good. It is a domination set. Okay? It is a domination set. Right? Similarly, other way, you take any domination set over here, fix the same domination set here, plus all this third layer points, it will become a strong geometric set, right? Okay, right? So it is a one-to-one correspondence from a domination set with the same domination points, and if you add the independent set, it becomes a strong geometric set. Converse, you fix any strong geometric set here, any strong geometric set, okay, any strong geometric set minus the third layer vertices, it will become domination set. Okay, so there is a one-to-one correspondence. Okay, so with this already domination set is NP complete. So there is a one-to-one correspondence between domination sets and the constructed graph with the help of the given graph. So the conclusion is the newly proposed problem, strong geometric problem, is also NP complete. Okay, so that's the conclusion. Yeah. So NP complete means we have a lot of challenges to go further, right? Yeah, this is actually a reduced case, like a caudal graph. Okay, caudal graph means the maximum cycle is 3, right? Maximum chordless cycle is 3. Okay, maximum chordless cycle is 3. Actually, here this is also a cycle, but between there is a chord, right? So it contains only triangles as maximum chordless cycle. Okay. So here, this is the graph form. Now we are restricting. So for general graph is NP complete. Okay. So general graph it is NP complete means suppose you are taking some restricted family. Can you say it is again NP complete means need not be. Okay. Say for example, the strong geometric problem is NP complete for general problem, but strong geometric problem is polynomially solvable. Actually, it is linearly solvable for tree families. Okay. So suppose you are proving for general problem means we cannot conclude the proposed problem is NP complete for any particular family. Again, you have to prove NP completeness for the particular family. Okay. Now we are taking this particular family like the caudal graphs. Okay. So caudal graph. So there also, so what is already proved concept we are taking is domination concept. We are taking a guy, right? Okay. And here we are constructing the new structure. I told you, so this is the caudal structure, caudal graph. And the newly defined structure also should be a caudal graph. Okay, should be a caudal graph. In that way, you have to construct the structure, right? So here triangle, actually here also actually the maximum caudal cyclist triangle here. You can check, right? Okay, you can check. Here triangles are there, maximum caudal cycle. Yeah. So here we are fixing one point. We are connecting with all the vertices of the given graph. Then you are extending to path of length to with this vertex. You are connecting all the vertices here, and again its independent set is there. Now actually here there you are taking domination set. So here you are taking independent set and this point plus some points you have to take here. So it will become a structural set. Okay. Converse also. So for caudal graphs, that family also it is NP. Okay, this is the post structure. Yeah. The next one is actually edge geodetic, strong edge geodetic. Strong geodetic means it covers only the what is this? Covers only vertices, right? It covers only vertices. Suppose we are having some kind of edges. See the same structure. You are having some kind of edges. Edges, some kind of cross edges. So in the vertices only you can cover only vertices. Okay, this section. So to cover this type of edges, we require some more points. So here, like a edge domination set is there, edge domination set. Here we are considering edge geodetic number. Okay. So here the edge geodetic number is also NP complete. So this is the structure. Somewhat complicated structure. Actually, this is not a complete graph here. No, it is kind of a graph like here we are extending 3. Actually, in the original graph, this degree of the vertex is 3. Okay, so here extending 3. In the original graph, vertex is 1, degree is 1. So 1 extension. In the original graph, the degree is 2. We are having 2 extension. Okay, so then actually here with this all these vertices we are connecting. Suppose here 2 vertices are there, here 3 vertices we are connecting because in the original graph it is connected. Okay, so basically it is not a complete graph. It is some kind of graph with some complicated structure, right? Yeah. Now the question is, what should be the base problem in the original graph? Definitely no domination problem. Okay, so domination problem there is no use. We are considering a kind of problem. It is called shortest path union curve problem. That side. Okay. Shortest path union curve means actually suppose this is the graph. And you are taking some collection of vertices. From this vertex, you can go to any point of the outside vertices, and you can connect by path, and the path should cover, this path should cover the remaining vertices. Okay, the path should cover remaining vertices. Is it okay? It is like spreading from this collection to any path. You can take any number of paths. In the other u irukna, so here you take some outside vertex v means between this u and v, you can take any shortest path. Okay, so in that way, you have to take the paths from vertex S to V minus S, shortest paths. In that path, you have to cover all the vertices of G. Okay. The question is, how many minimum number of this type of vertices required? That number is called shortest path union cover problem. Okay. So the shortest path union cover problem is NP complete. Right. Shortest path union cover problem is NP complete. So with the help of shortest path union cover, we prove this edge geodetic set is also NP complete. Okay. Actually, Dr. Paul Manuel and our group constructed this complicated structure I told you. So recently my student, research student, Dr. Deepa, now she is working in St. Joseph's University, Bangalore. So we constructed some basic structure to prove that. No? Yeah. Yeah. This is cotton graph. Yeah, this is a kind of simple structure, right? Simple structure. Using this structure also we can prove the strong geodetic edge problem is integer. See, compare it. This is some more complicated structure because it's the second layer, right? So some more basics. Actually, this is some simple structure, right? Okay. So there, what we are taking means we are taking vertex curve problem. Okay. So on the basic graph we are taking vertex curve problem. With the help of vertex curve problem, we are proving this constructed graph has a strong edge geodetic edge. Okay, so these are some inequalities related to edge geodetic system. So the readers, suppose you are interested in so you can go through the literature, right? Okay. Now the next, actually these are some of my research students' topic. From the geodetic problem, so we can extend to any number of problems. No? So here we are extending to strong K geodetic problem. Okay, strong K geodetic problem. Strong K geodetic problem means actually here we can take any length geodetic of any length, right? Okay. So K means no, you can consider only geodetic with the distance K, right? So what? Every strong K geodetic set is a strong geodetic set, but conversely not it. So actually here K is less than or equal to diameter of the graph, right? Yeah. So this is again the complexity concept. So actually it is a very simple construction, very simple construction comparing to the other constructions. So there we are taking domination section. Suppose we are taking K geodetic problem means you take K minus 1 length path here. K minus 1 length path. So K minus 1 count pannom. Then one distance bound. Okay, one distance we have to go, right? Second distance bound here. From here actually it's not a shortest path, right? So the thing is, but in the previous first case we can even stop this base. But in the it has to go up to here, right? Okay. So what we are taking is so they are actually total domination number we are taking, right? Total domination in the concept total domination. So with the help of total domination, we can prove here this K geodetic problem is NP complete. Okay, so this is the structure. Total domination and here K structure, right? Okay, so these are some bounds. Yeah, the proof is very simple. Suppose we are taking K geodetic means so. Suppose S is the K geodetic set. Okay, then this bound is obvious. Actually, what is the LHS? Left hand side. N means number of vertices in the graph minus the cardinality of the K geodetic set. Okay, this much number of vertices should be covered. Okay, should be covered. Now you have this much number of geodetic, right? Okay, so how many possible geodetic means NC2 geodetics are possible? Okay, each geodetic covers how many points? It is a K geodetic, length K. So every maximum cover pannom. It may cover K minus 1 points. Okay, so this is going to be the nature of the bound. Even you simplify panning, you will be getting the true answer, right? And these bounds are sharp. Bounds are sharp for C and V and equal to 3. So similarly, this is geodetic set and other variants are defined. Okay. So these are some variants. So here we are extending the concepts to geodetic set. So many concepts to product graphs also. Okay. So we are considering bounds with bounds with the help of SSPCU. SPU means shortest path union cover problem, right? Okay. Here SSPCU means strong shortest path union cover. Okay. So I told you from this vertex, you can go here. Any number of paths are taken care of. Strong shortest path union cover means from one point, outside points, you can take only one path. Okay. With only one path you have to cover. So that is called a strong shortest path union cover. One of my students worked on that. Actually, we proved the strong shortest path union cover is also NP complete. The construction is there. I will show you. Okay, so these are all some bounds and product graphs. This is the realization construction existence, you can say. Okay. Actually, the whole presentation is based on one of my students' thesis. She is called Dr. Deepa. Now she is working in St. Joseph's University, Bangalore. 70-80% of the works are from her work. So these are all from her work. Now we are taking particularly K geodetic, I told you, no? So we take K is equal to 2, we are considering edge geodetic, right? So here the beauty is, if you consider edge geodetic means, if you consider the Sierpinski graph means, strong edge geodetic means we have to consider all the vertices, okay? We cannot minimize all the vertices we have to consider. Yeah. Now we are constructing some construction. Yeah, this is any graph. Any graph we are constructing this graph. Actually, this structure is Sierpinski structure. So for each edge you are replacing by Sierpinski graph of any order, right? So maybe this dimension is 2. You can take 3 dimensions. One edge is replaced by one Sierpinski structure. Now this is some new structure. Now the question is, what is the strong 2-edge geodetic number means? For this graph, newly constructed graph, you have to take all the vertices. There is no other two. Similarly, this is another structure. Similarly, here, structure is there. So all this structure, actually here we are replacing vertices and edges by Sierpinski structure, right? Okay. So the thing is, suppose the newly constructed graph, what is the strong edge 2 geodetic means? We have to take all the vertices. That's what we are saying, right? Strong geodetic 2-edge geodetic means, so it is going to be order of the constructed graph, right? Okay, so these are some results. Yeah, I told you, the strong sort of spot union cover problem. So it is NP complete. So this is the structure. This structure goes like this. So actually here given what is the survey means? We are subdividing into 2 points. Every so this edge subdivided into 2 points. And subdivided vertices are connected with this vertex, and the original vertex are connected with this vertex. Then we are adding one triangle over here. Okay, so with this structure we can see strong short spot union cover problem is NP complete. Then we are taking domination sector. So here short spot union cover. So it is going to be strong. So it is going to be NP complete. So the structure. These are some properties. This is some realization for any given number again, and strong short spot union cover is B, and short spot union cover is A. So with that we can construct a graph. Okay, so it is like the existence. Okay, so actually again we are talking about K short spot union cover. So here you can take any short spot of any length. So we can restrict to K. We can restrict to K, right? Okay. So that is called a K short spot union cover. We define, our research group has defined all these things, and they have proved this is NP complete also. And here this is a beautiful result, right? See, this is the lower bound for this strong short spot K union cover. This lower bound. How the lower bound is? See, if you read, you can understand it. Suppose so here you are starting with one vertex pin, so you can go up to this K length, in multi dimensions. So from this, how many branches also you can go? How many directions you can go? So maximum delta times, you can branch out. Yes or no? Right? So that's what this delta, right? And from this, how many times you can branch out? Again, delta times you can branch out, no? Right? So in delta times branch out already this is counted in the previous case. So in delta minus 1 count out. So that is here, delta into delta minus 1. Okay. Similarly, it is branching out. The next time branching out means it is delta into delta minus 1 whole square, right? Okay. It goes up to K minus 1 times. This is the K shortest path, right? So K minus 1 times. Okay. So if you simplify this, so it is a geometric sequence. So simplify, you'll be getting like this. If you again simplify, you'll be getting like bound, right? So it's a very simple observation. So I encourage the research students, particularly doing research in graph theory. So this kind of observations are very, very important. இப்போ கிராஃப் தேரியில் பண்ணுறவங்கலாம் என்ன பண்ணுறாங்கன்னா ஹைப்பர் கியூப் எடுத்துக்கிறாங்க அப்படியே எடுத்துட்டு actually your work is very hard, I appreciate, but is it innovative means the question mark, right? Okay, so the innovative, actually this kind of innovative things also should be included in your thesis, right? It will be appreciated. Okay, because this kind of concepts are available everywhere. Even you can take up any variants of domination set or any variants of covering problem. Still this kind of constructive things are available. The thing is, you have to find out where it is available. Okay, fine. Yeah, actually, so we have started this bound, no? So this bound is short here, okay, for this particular graph. And other bounds are there, okay, I'm not explaining all these things. Actually, this K shortest path union cover is also NP complete. This is a very simple logic. Actually, in the previous NP complete construction, and here also, only this structure, we are extending this structure. Other join. So here K minus 1 times we are extending, okay. So with this simple extension concept, we can prove this NP complete, okay. So these are all some properties. Actually, here, another one is, actually these are all the things, our research group has done. We are considering monophonic problem. Monophonic means it is not a shortest path. Actually, the monophonic concept is required for Chennai city particularly. See, for example, I am traveling from Loyola College to T Nagar means, every time I cannot prefer the shortest path. Okay, shortest path means through T Nagar I can go directly, but sometimes due to traffic I have to select the alternate path. It may not be the shortest path, right? May not be the shortest path. Okay, so that type of path also sometimes we have to take. So that is the monophonic concept. Monophonic path is not a shortest path, but it is not a chordless path. Monophonic path should not contain any chord between that. Okay? So chord means suppose you are going some path means so then the vertices are there means there should not be any direct connection. Okay, so the chord should not exist. So that type of path is called monophonic. And our students worked on this also, some monophonic and total monophonic, and the NP complete construction is totally different. You can see the previous cases, this case is totally different. Actually, it is that is again a somewhat complicated problem. Okay, so available in the literature, it is published paper. You can go through that. Now the next concept is connected geodetic. So these are some properties. So actually, connected geodetic, actually like domination, we are defining different variants. Connected means if the induced graph will be connected. Okay, so that is called connected geodetic. The geodetic set induced graph is it will be connected, and again it is NP complete for various graphs. And this is the bound for that. Also, the arguments are there. I think. The beautiful arguments here. I think I can spend some 1 or 2 minutes on explaining. So connected geodetic means basically it is a geodetic set, a strong geodetic set. Only thing is it is connected between. It is connected, right? It is connected. Okay. The induced graph is connected. The induced graph is connected. Okay. How we are creating this bound means. LHS means S is the connected cardinality of connected geodetic set, and N is total number of graphs, N minus S. It is less than or equal to in S. How many different paths are available? Means NC2 paths are available. So minus this S minus 1. Why this S minus 1? Minus S minus 1. This least number, right? Since it is a connected geodetic means suppose these two vertices are adjacent, it is not covering any outside vertices. Yes or no? Okay, so even though it is in the geodetic set, since it is connected, if these two are adjacent, it is not connected, it is not covering any outside vertex. Okay, because this is not shortest path, this is the only shortest path, right? So even though it is in the geodetic set, suppose x1, x2 is there, means there is no use of x1, x2. Okay,
So how many this useless edges are there, useless pairs are there means, what is this? It is, we are taking the minimum, okay, we are taking the minimum. Since minus means so, we are taking the minimum. That is the s minus 1. S minus 1 edges, s minus 1 edges are, edges means s minus 1 pairs are useless pairs. In the pair of the useless pair, yes or no? Okay, that's what we are saying. S minus 1 pairs are useless pairs, right? Okay, into d minus 1. Okay, so there are SC2 paths are there, minus S minus 1 pairs are useless pairs. Okay, fine. So effectively SC2 minus S minus 1 pairs are there. Each pair can cover maximum D minus 1 vertices. D is diameter, right? So if you simplify, you'll be getting that inequality. Okay. Okay, fine. So these are actually this boundary start for this particular graph form, and similarly edge version, and here we are classifying. So here graph G1, G2, G3, and here this particular actually we are taking the subgraph now. Actually, this is the geodetic connected geodetic sector. This connected geodetic sector. This connected geodetic sector. If you find the diameter, actually connected geodetic sector. In this connected geodetic sector, you take the induced graph. In that induced graph, you take the diameter. The diameter is less than the grid structure. But here, the connected geodetic sector induced graph diameter is equal to the original graph, right? Okay. And in the next structure, the connected geodetic sector, its diameter is greater than the induced graph. Okay, I'll complete. Greater than. Okay. So connected geodetic sector, the induced graph diameter may be less than the diameter of the original graph, may be equal to the diameter of the given graph. Sometimes it may be greater than the diameter of the given graph. Okay, so three categories are there. With the three categories, we are classified and we are studying, and so many things we have studied. So based on that only, right? Then we are going to product graphs. So these are all that students' thesis. Okay, so these are all the results. Yeah, next one is hull number concept. Yeah, it is a hull number. A hull number is a separate concept due to the time restriction. You can see in the literature, it is almost equal to geodetic, but it is not geodetic. It is totally the convexity concept. Okay, so parallelly we are defining strong hull number concept, and we are proving the complexity part. It is a highly complicated one. Okay, so this is the final constructed graph, right? Okay. Actually, here we are using the three-set product. We are not using the polynomial reduction from the given graph. Three-set. So it's actually the basic structure is that from the basic structure we develop this structure, right? Okay. So with this three-set concept, so we proved it is NP complete. So it goes like this. Actually, we try to publish this paper due to proper reviewer is not possible. Actually, we considered some kind of complicated things, so no reviewer is ready to go through all these things. Still, it is pending. Okay. Yeah. So these are all some particular graphs. So we have varied strong. It is a butterfly, right? We did it hull number, and then geodetic propagation. So many other things are there. Okay. I end up with now people are trying this fuzzy geodetic concepts. Right? Now the first question, I told you, suppose you are starting some problem in Zoom, with that problem, whether it's there any application. So that you have to see. Right? Okay. So fuzzy geodetic means actually, geodetic means here these 2 points are well defined now. Between that we are talking about shortest path. Right? Okay. In fuzzy means even these 2 points are not well defined. Okay. Right? Say for example, one point was well defined as one, but maybe the next point may not be well defined sometimes, right? Say for example, like a movie Manjimal Boys. Maybe we can guess, right? Okay, so that is fuzzy actually, right? That is fuzzy. So in reality, that happens. but it is in the very beginning stage. Any researchers are interested means I have only some 10-20 papers are available. You can start research. So okay. Even in our United States, they bomb blast Mananglia, some nuclear, so within the underground, so they are not able to track exactly that nuclear plants, okay? So they are not fully succeeded operation. So let me first the concepts, right? Okay, so I end up with this. So a lot of scopes are there still, so researchers are interested in it, so you can start. The only thing is publication problem, because finding researchers, reviewers is very difficult. If you have any reviewer network means, you can start. Still so many things are there, right? So these are my references. Any questions? So Dr. Arul also did research in that area only. He covered so many things. So he tried to connect coloring concept with geodetic concepts, and he tried open geodetic with domination. So many things. Even domination with geodetic also he tried so many things. Okay, very good. Thank you. Any doubts?
I now kindly request Dr. G. Meena Devi, Professor and Head, Department of Mathematics, to felicitate our Chief Guest, Dr. D. Anthony Xavier, with a memento. Now I call upon Dr. K. Abhinaya to deliver the vote of thanks.
Thank you, sir, for enlightening and thought-provoking session on strong geodetic problems in graphs. Your clear exposition of complex concepts and your deep insights into graph theory have truly enriched our understanding. The session was not only inspiring for researchers and academicians alike. On behalf of the organizing committee of IC CAMSHIA 2025, I express our sincere gratitude for your valuable time and meaningful contribution to the conference. We truly appreciate your presence and look forward to continued academic interactions. Thank you, sir.
The participants of session 13 presentation are requested to go to the MBA Blocks Conference Hall for the presentation. I repeat, the participants of the technical round of session 13 presentation are requested to go to the MBA block. MBA Conference Hall.
Another study from real number we are studying the complex number, but it is totally different complex number. For example, in complex there is no order in base. Here in real number, actually 3 is greater than 10. So that kind of so many things are there. Monitor the extension, we can go velocity, we can order. Yeah, for the yeah. the session.
Participants anybody who have missed the session 9 presentation can go and join session 13 in MBA Blocks Conference Hall. I repeat, participants who have missed the session 9 presentation can go to session 13 in the MBA Blocks Conference Hall. I now request Mr. S. Maniganda Prabhu, Assistant Professor, Department of Mathematics, to introduce the chief guest.
Very good afternoon to one and all present here. It is indeed my privilege to extend a hearty welcome to Dr. Prabhu sir, Associate Professor, Department of Mathematics, Rajalakshmi Engineering College. He completed his undergraduate, postgraduate and PhD studies at Loyola College. His PhD was supported by the prestigious major research project from the University Grant Commission. His doctoral work focused on graph theory, a subject where he continues to make groundbreaking research. Over the years, Dr. Prabhu sir has become a recognized figure in graph theory with over 75 publications in Science Citation Index Journal. The profound impact of his work can be evidenced by Hutch Index of 15, reflected both the quality and citation strength of his contribution. His academic excellence has been recognized with multiple awards, including the Best Teacher Award and the Award for Research Publication since his joining Rajalakshmi Engineering College. And he is also a proud recipient of Ragzan Award for the Best Research Scholar, the UGC Junior Research Fellowship, and UNESCO HB Brain Game Initiative Award. Beyond this achievement, Dr. Prabhu sir has made substantial contribution as a research supervisor, guiding 8 PhD scholars to successful completions and mentoring several others. Currently, 6 scholars are pursuing their PhD under their guidance. His collaboration with internationally renowned researchers across South Africa, USA, China, Slovenia, and Indonesia further reflect the global relevance of his work. He serves as an editor as the leading journals such as Scientific Reports and PLOS ONE, and regularly reviews more than 25 reputed SCI journals. He also a highly regarded speaker, having delivered invited talks and guest lecture at numerous national and international platforms. Personally, I take pride in being a research scholar under the esteemed guidance of Dr. S. Prabhu sir, whose mentorship has been instrumental in shaping my academic and professional journey. Over on you, sir. Thank you, sir.
I now cordially invite Dr. S. Prabhu, Associate Professor, Department of Mathematics, Rajalakshmi Engineering College, Chennai, to deliver the seminar. Welcome, sir.
Good afternoon. First of all, I would like to thank the organizer for giving the opportunity to share some of my research experience at this gathering. As Manish said, I'm holding a fellowship with several other credentials. This is not simple work actually. I started my research career in the year 2010. From that, we started learning the concept called multi-dimension. Now it is almost 2025, around 15 years of journey. The same subject. My professor used to say, whenever you do research, you should not dig in different places. You must dig in the same place in order to get water. If you dig in different place, at any cost of time, you won't, you will never get water. So that is the same inspiration and motivation. I started digging
my own content called multi-dimension for the 15 years, and around the 12th year we got the water. So that I would like to say, because there are several other seniors of mine in the same area of multi-dimension and relevant field, whereas they able to close all the class of graphs for which the values, the parameter values are obtained. And finally, they gave the last plate where there is no food, because everything is exhausted by the seniors. And while they suggest this topic, they themselves say everything is over, nothing you could achieve from this particular topic, because almost every graph classes are over. Unless otherwise you find a new parameter or a new graph class, you won't get any new results and new papers likewise. That is also there in one side, and my supervisor advice is also there in the other side. You must dedicate the same place. And later, we got a content, the content only we are going to see, and the entire journey we will see in this presentation. The topic is slightly, I have modified the content with respect to the new audience. The problem, the traditional name of the problem is multi-dimensional experience, but where it is applicable, where it applies, that I have given here as a title. The efficient way to represent the processes and their connections in an interconnection network. I hope you are all familiar with the interconnection network. This is your interconnection network where computers are connected with some CPUs and routers and etc. And you can very well connect any network with the help of Raspberry. The moment I introduce a network, the parameter has to be introduced. The parameter here I have taken is distance. How do I define a distance between two vertices? Is the number of edges required to connect the two vertices. Say example, take two vertices S and T. The number of edges, minimum number of edges, of course, required to connect S and T are here 2. So this is actually distance between two vertices. Distance between S and T is 2, where S and T are taken here as vertices. The next we define distance between only 3 small definition: distance between vertices, distance between vertex to an edge, distance between edge to edge. So with that we will start defining the problem. Next, distance between vertex and an edge. Select a vertex S and an edge F with n vertex X and Y. Now the distance between S and the edge F is given here as, first let us find the distance between S to the one end of the edge, say 2, and the other end of the edge Y. So S to X is 2 and S to Y it is 3. So what is the distance between S and F? It is minimum among these two parameter values. So I could be able to reach the edge F from S with using only 2 edges. Not another way. If I am able to connect the edge with the vertex with only 2 edges, and that is going to be the distance. So always we will have to consider the minimum. The next, edge to edge. Take 2 edges and the distance between edge to edge can be defined as, actually 4 parameter. Here I have restricted with one edge E with endpoints S and D and the other edge F, and I define the distance from S to F it is 1, T to F it is 2, and therefore the minimum is 1. So we can very well say the distance between two edge E and F is 1. So now we are clear with distance between two pair of vertices, distance between a vertex to an edge, distance between two pair of edges. Now what is the problem? network is clear, and the parameter what we are going to use is a distance parameter, that is also clear. Now we are ready to define a problem called resolving set. Now, let W be an ordered subset of a vertex at V of G is said to be a resolving set if the representation, see the representation is defined here. Representation of a vertex V in W is given as distance between the vertex V to W1, distance between the vertex V to W2, etc. V to Wk. So this is going to be a k vector because you are going to sense the distance from every vertex of W to a particular vertex of V, and we call this representation as the code of V. Likewise, we just give representation to every vertex of the network, and finally we say the set W could be claimed as resolving set if every vertex of G has unique representation. So that is what in the next slide it is given. A set W is a resolving set for G if any two distinct vertices U comma V belongs to V of G. The condition, the representation of U with respect to W should not be equal to the representation of V with respect to W. In the sense, at least one of the coordinate it must differ. At least one of the coordinate it must differ. And the other way we can define it like this: let V be the vertex set and W be the subset of a vertex set. And now any two vertices outside the W, at least there exists one vertex inside the W such that they are at an equal distance. If you have at least one vertex inside W and that vertex will differentiate the code of the vertices U and V. So that is the logic behind. And of course the parameter is called the metric dimension, and we call that as the minimum cardinality of a resolving set. Otherwise we call the basis. The basis is the subset of vertex set which helps us to generate codes for all vertices of G in the minimum manner. Illustration. Consider this graph, and we can also explain the complexity of the problem in this graph itself. There are 6 vertices and 7 edges. Of course, our resolving set is a subset of the entire graph. So you must pick the subset from the vertex set containing 8 vertices. How many possible subsets we can generate from this 8 vertex graph? That is a basic set theory question. There are 2 power cardinality of the vertex set. There is 2 power 8 number of subsets you can generate. Of course, in which empty set and whole set can be removed. Therefore, 2 power 8 minus 2 number of subsets could be the resolving set of this particular graph. But 2 power 8 minus 2 number of subsets cannot be exercised here. So that is the complexity of the problem, because for 8 vertex graph, you can very well find the answer in 1 or 2 day timing. But what happens if you have more number of vertices in a network? When I say 50 vertex network, so a network is given with 50 vertices, can you able to find the resolving set for the 50 vertex network? So it would be 2 power 50 minus 2, which is not practically possible. Even if you write the code or program, the computer may not able to run its components and finally give the solution. So that is why this problem is considered to be an NP complete problem. The metric dimension problem is an NP complete problem. The problem is clear. You need to find the subset from the vertex set, minimum subset or with the minimum cardinality, satisfying the condition, generating the code for all the vertices of G or V of G in V of G, such that they are unequal. So let us consider the first vertex, which means I select that vertex and put it in the W. From that, if I start giving the distance to the other vertices, it becomes 1, 1, 2. Now, we are unable to give distinct representation from the vertex marked red here, because there are 3 1s and 2 2s, which means you don't have distinct representation for the vertices of G. So you need to require one more vertex, let us say green color vertex, and you put that green color vertex in the W. From that vertex, if you start distributing the distance, it will be 1 1 2 1 0 1 1 0 2 2 1 1. Can we say the graph is resolved with these 2 vertex? No, because there is a top left vertex with the 1 1 code and the bottom right vertex with the 1 1 code, right? Top left vertex with the 1 1 code, bottom right vertex is again with the 1 1 code. Still the graph is not resolved because you have 2 vertices receiving the same code, which means 2 processors receiving the same representation. So we need one more. Let us take third vertex with the blue and start giving distance between these. And now the graph got resolved by all the vertices receiving the different representation. Now the next question is, I have given you a vertex set, a subset with 3 cardinality. Is it possible to reduce further? Which means, can I able to get a subset of lesser cardinality than this, which can resolve the graph? So in that sense, if I start searching for the other vertex, if I, instead of fixing red vertex in the middle, if I fix it on the top, I get these representations, and the green vertex on the top, I get these representations. Now, if you look at the graph, all vertices are receiving the different representations. So the earlier case it was 3, the later case now it is 2. So which is best answer? 2 is the best answer. The next question would be what? Can I reduce further? And there is a strong result which says whenever you get the metric dimension 1, the graph should be a path. Or whenever you have a path, the metric dimension is 1. It is a two-way result, that is called if and only result. Metric dimension is 1 if and only G is a path. And therefore what you can say from that result, the answer for this graph cannot be 1 because this is not isomorphic to path. So therefore, from the result, metric dimension is 1 if and only G is a path, we can say the graph will admit the value greater than or equal to 2. By exhibiting these 2 vertices resolves this graph, we can say the value is less than or equal to 2. So both when I combine greater than or equal to less than or equal to, I can able to achieve equal to 2. So for this graph it is 2. The next thing is whether I can able to again reshuffle the vertices with the same cardinality 2. I can able to get any other investigation. In that sense, I can able to achieve the same cardinality subset. But in the earlier case, the 2 vertices are independent. Now the 2 vertices are adjacent. So connected resolving set. This is another parameter in the literature. How best you can connect the vertices of the basis. So when I compare all the 3, it's just a resolving set, minimum resolving set, and the last one is connected resolving set. Sometimes you may not be able to get the minimum resolving set as equal to the connected resolving set, because to maintain the connectivity, you may have to include some more vertices which will violate the cardinality of the minimum resolving set. The concept and its relevance. In the chemical compound, if you want to give a distinct representation to distinct compound, you can very well use this concept. And in network discovery, you may not be given with the exact information of a secret network in the beginning stage. What they do, they will say just this many vertices, but you will not be given with whether there is a link between the pair of vertices or not. So without having the information, with the help of only the codes, you can able to generate the link between the vertices. So this is what your network discovery and verification. You will be initially given with a set of vertices, and you will not be given with any edges, and you will be only given with the codes, and that too generated from the vertices. And with the help of code, you need to just construct the edges, and finally the network will be discovered. So in the network discovery also, you can just have application over multi-dimension, and there are plenty of other applications, mastermind game and other geometric routing protocols, etc. So that is why this problem has a very rich literature. It started in the year 1975. Till then results are coming, and not only with the Indian people, all the multi-dimension quality research papers are coming from the developed countries. So these are the applications. There are plenty of applications. I have listed few. History. In 1975, the problem is defined with Slater under the name locating set or reference set, and the same concept was rediscovered with a different name, Harare, with the Harare melter, and Charton the same year they started defining the same concept with the resolving set and minimum resolving set. All the three, in 1975 there is no communication, so all three authors are from different countries, so they themselves developed their content and they published. Once we get a network, later only we come to know all these problems are one and the same. Few literature with our Indian researcher, 2008, they have identified values of multi-dimension for butterfly and Venus network, and 14 for directed graphs, and 18 for some chemical structure, in 17 permutation graphs, 14 generalized Peterson graphs. These are all graph classes for which the multi-dimension is investigated, and there are several other graph classes. Even now we were not able to get the multi-dimension. One special example is hypercube. Infinite graphs, interval graphs, field related graphs, circle and Harare graphs, honeycomb networks, generalized batteries are the few interconnection networks for which the value parameter is investigated with different papers. And now I started searching for variants of multi-dimension. I could able to find 4 variants, of which 3 I have taken here. Then later there are several variants in multi-dimension. We considered only 4 here, and the 2 mixed multi-dimension we just started. So fault tolerant multi-dimension, edge multi-dimension, and fault tolerant edge multi-dimension, and of course mixed multi-dimension are notable variants of multi-dimension when compared to the other variants, because there are a lot of research going on these 4 variants, and many standard papers are coming in these 4 areas. Fault tolerant multi-dimension. So here it is already the problem is NP complete. Here another tough one. When you fix with the resolving set, how they give another condition is, if you remove any one vertex from the resolving set, the set must still be able to give distinct code to the vertices of G. So that is the idea. A resolving set F of the graph G is a fault tolerant resolving set. If each V in F, any V is getting fault, that is what V minus F. So F minus V. Any vertex from the F is getting repaired or disappeared, you can still able to give code for all the vertices of G. So that is what your fault tolerant resolving set. The obvious bound is going to be multi-dimension plus 1 is going to be the value, right? So 1 is getting fault. The remaining vertices should be able to give or generate code for the entire network. Means obviously you must have a comparison between multi-dimension and fault tolerant multi-dimension with at least increase by 1, but not necessarily exactly equal to 1. This is one thing. For every 2 vertices outside the F, there exists at least 2 vertices inside F. They give distinct representation to X and Y, or unequal distance from X and Y. Suppose if you get fails, we will take care of the task. We will give different distance to X and Y. In the same sense, V is getting fail, you will give different distance to X and Y. neighborhood. It's a very simple and traditional definition in graph theory, neighborhood. When you take a vertex U, the open neighborhood of U is going to be collection of vertices in V of G such that U and V are adjacent. That is open neighborhood. When I say closed neighborhood, the open neighborhood includes the vertex itself, U, called closed neighborhood. So using this neighborhood content, we were able to achieve one tool, and that tool gave a beautiful results for us. Two distinct vertices U and V are adjacent twins if the closed neighborhood of U is equal to the closed neighborhood of V, and non-adjacent twins if open neighborhood of U is equal to open neighborhood of V. The term twin is our common used term. When I say twin brothers, they will have same parent. Likewise, when you say two vertices are said to be twins, they will have same common neighborhood. You can see this diagram. Look at here, two pink vertices. The neighborhood of the pink vertex, one particular pink vertex is adjacent to all the four yellow vertex. Similarly, the other pink vertex is also adjacent to all the four yellow vertex. You can say the neighborhood of one particular pink vertex is equal to the neighborhood of the other pink vertex. And moreover, here they are adjacent, therefore they are called adjacent twin set. And the right side, you have non-adjacent twins like this. So neighborhood of one vertex is equal to the neighborhood of the other vertex. So this topology, that is, whatever the network you take or whatever the graph you take, suppose if you have this particular topological property inside that particular network, you can very well state our lemma or apply our tool to get the answer in a short period. Look at here, twin sets. The top one together forms a twin set, and the bottom one together forms twin set. Is very simple. In the particular set, if you take any two vertices, the neighborhood should be same. Or you have to say any two vertices if you pair, they must be twin. First and second twin, first and third twin, first and fourth twin, 2 and 3 twin, 2 and 4 twin likewise. Of course, in the yellow color vertices, any two yellow color vertices if you take, the neighborhood is going to be what? The pink vertices. Similarly, for pink color, any two pink color vertex, any pink color vertex if you take, the neighborhood is going to be the yellow vertex. So in that sense, you can say the top layer gives a twin set, the bottom layer gives another twin set, because any two pair in that particular set is a twin. So this is the result by Hernando. U and V are twins in a connected graph G, then distance between U to X is always equal to distance between V to X for every X belongs to V of G minus U and V. The U and V are twins, and of course because of the twin property, they don't have connectivity apart from its neighbor to any other vertices of G. So in that sense, if you want to travel to U or V from anywhere, you must travel via the neighborhood. So along with the neighborhood only, you can just travel and then reach your U and V. So that concept gives you the distance will be always equal with any other nodes of V of G other than this U and V. So with this, we have developed, see here, this is a equivalence relation. If U, V, W be three distinct vertices of G, U and V are twins, V, W are twins, then U, W are also twins. Because neighborhood of U is equal to neighborhood of V, neighborhood of V equal to neighborhood of W. When I club, you will have neighborhood of U equal to neighborhood of V equal to neighborhood of W, and therefore all the three are twins. Likewise, you can start generating the twin set with more number of vertices, and finally you can end up with the whenever the condition violates. Whenever the other vertices are not obeying the property, you can violate, you can stop and then declare that is the maximum twin set you can just generate from the graph. And obviously, there could be more number of twin sets, more distinct twin sets in a graph that I will just share in the next slides. So this is another one. U and V, the twins in a connected graph G, and W resolves G, then U or V should be in W. Moreover, if U is in W, V not in W, then if you remove U from W, the V can be included. So you can say if U and V are twins, U will take care of the duty of V as well as V will take care of the duty of U. So that is the corollary one. So from that we were able to give a lower bound for the general graph G with any number of twin sets in a G. The dimension value, that is multi-dimension value, is greater than or equal to sum of all twin vertices minus the twin sets, the twin set number. Because you can just say in any twin set, all but one vertices will contribute to the resolving set because of the equality. So this paper we got published in 2018, and that is the first SCA paper we published in the area of multi-dimension after 8 years of journey from 2010. Since then, we have successfully using this lower bound, powerful lower bound, for all other graph classes, we were able to successfully get the exact answer for all other networks. So once we found that answer, we were able to identify some of the paper in the literature with some mistakes. For example, this paper with the Mathematics Journal, they have classified a graph class for fault tolerant multi-dimension admitting the maximum order, that is n. Here in this paper, they say the characterization theorem by Raza et al. In 19. See, we got the answer in 2018, which says what? All but one vertices will contribute to resolving set. And what is the relation between the resolving set and the fault tolerant resolving set? Any vertex in the fault tolerant resolving set is getting failed, still the set should be able to generate the codes to the graph, right? So in that sense, I say there could be at least one vertex more than the resolving set to generate the fault tolerant resolving set. But in this paper, they say the fault tolerant metric dimension is n even only if the graph is complete. So they have just stated this result by referring the previous result. The dimension of n, metric dimension of G is n minus 1 even only if G is complete. That is result by equivalent to path. So if metric dimension is 1, G is even only if path. Likewise, metric dimension is n minus 1, then even only if G is complete. So by referring that paper, and I told you there could be at most maximum at least one vertex increased, and the graph order is itself n here. So what is the maximum number you can increase from the metric dimension to the fault tolerant metric dimension? It can be 1. So the answer is correct, but the graph class what they restricted here is wrong. So the n value will admit not only for complete graph but also for several other graphs, and that they fail to mention in this paper. You can just see dimension dash, that is fault tolerant metric dimension is G equal to n, metric dimension of G equal to n, even only G is complete. And I could very well give a counter example for this graph, which is complete bipartite graph. Take some 2 vertex and 3 vertex, complete bipartite graph. You will require all vertices to form a fault tolerant basis, and that small counter example gives me another literature correction. This is another paper where again the fault tolerant metric dimension was given wrong, and both the paper results we have taken. So this is actually during 2020s. The paper got published in 2019, and we observed that there is an error in the paper in 2020. At that stage, we had only one paper, only one SCA paper. We were not confident enough to write to the journal saying that these two journals were giving error result, and we are giving the correct result. So we are very beginner researcher. Though there are 8 years past, 2010 journey started, 2018 the first paper published in SCA, and we got this paper in 2019, and 2020 we got this error. but we don't have confidence in writing the journal saying that this paper has an error and we are giving the correct answer. Then later we investigated this network, and this particular network was investigated in that IEEE Explore journal, and it's a very good journal, Q1 journal with more impact IEEE access. So here again, they gave an answer, fault tolerant. See, actually for this network, the metric dimension is always already investigated by my own guide, my own supervisor at Loyola College. They found the answer for this particular graph with respect to metric dimension parameter. Fault tolerant metric dimension parameter is introduced in my period after maybe 2008. After 2008 only the fault tolerant metric dimension came into the picture, and that time they have closed the topic of metric dimension in Loyola College. Then later when I see this paper, and I got that the dimension dash, that is fault tolerant metric dimension, is less than or equal to 4 into 2 power r, and there is another conjecture because they are not able to give the lower bound, they were able to give the upper bound. Upper bound is very simple. If you just pick some vertices and if you are able to get the code and we can declare that is the upper bound, definitely the answer will be less than that. But in lower bound they were not able to achieve whether the answer will be greater than or equal to 4 into 2 power r. So in that case what they have done, they just simply state that as a conjecture. You all know what is conjecture. What is conjecture? It is neither proved nor disproved. So they have just stated as a conjecture saying that the fault tolerant metric dimension is greater than or equal to 4 into 2 power r. And with our technique, the twin technique, we found this is again error in the IEEE access, and we got this error, or we identified this error by visualizing the same graph in the other version. This is also another paper proved by our own beloved guide, Dr. Bharati ma'am, and she has given a different representation for this particular butterfly network as a diamond representation in the crossing number problem. In that diamond representation, we can able to see visually the existence of twins in the graph, whereas here we may not able to. So when we look at the same graph, the isomorphism between these two graphs were proved in another paper which came in discrete maths and theoretical computer science in my period itself. So I got that paper and I just compared these two, and I myself convinced that this graph is isomorphic to this. Therefore, if I am able to find the fault tolerant metric dimension for that particular graph, and that will counter this particular existing IEEE access paper. So here I can able to locate the twin set like this. The encircled vertices, the 2 pair, will form a twin set. And I told you all but one vertices of the twin set will contribute to basis. All vertex of a twin vertex will contribute to fault tolerant basis. So no other vertices from outside the twin set will take the act of the vertex in the twin set. So only replacement or replacer is going to be in the twin set itself. So you might have left one vertex in the twin set among the twin vertices in order to form a twin basis. For fault tolerant construction, the leftover vertex also should be included in the basis set in order to claim that as a fault tolerant basis. Beyond that, you cannot include some more vertices outside the twin set to form a fault tolerant basis. So that is the logic and small observation we obtained, and with that observation we try to write my answer as 2 power r plus 1. The earlier answer was 4 into something, right? 4 into 2 power r. 4 into 2 power r is actually what? 2 power r plus 2. 4 into 2 power r. So you can write 2 square. So 2 power r plus 2. They say 2 power r plus 2 is the upper bound, and even that is not proved with the lower bound, the conjecture. So they say 2 power r plus 2 as the answer. By just along with the conjecture, you can very well say the answer is 2 power r plus 2. Whereas my answer is 2 power r plus 1. So what is the difference between 2 power r plus 2 and 2 power r plus 1? It is exactly opposite. Exactly opposite. So this is the first answer we got. And in the same paper, there was another interconnection network discussed in the paper. called the silicate network and Bennett's network. So this Bennett's network, they gave the answer 13 times 2 power r minus 1 and 13 times 2 power r minus 1 as a conjecture for the lower bound, and again that is also wrong. Bennett's network is redrawn in the different way with the diamond representation, and I can able to find the twin sets here, and with the calculation of twin sets, number of twin sets and the number of vertices in each twin sets, I can able to get this result 3 into 2 power r, 13 into something, 3 into 2 power r, and I am able to get answer which is drastically reduced from the earlier answer. And several times we have just because when we write it to the journal, we must be double sure that whether the answer is correct or not. Several times with the several scholars we have just validated, and the answer is our answer is correct when compared to the earlier one. Then later, the same paper, the network discusses silicate network. Here again, the answer is given between the bounds 6n plus 1 to 21n. And when I see here in the silicate network, it is very easy to observe the top level vertices will form a twin. You can see the corner vertices along with the inside vertex will form a twin. But in the the earlier case it was non-adjacent twin, whereas here it is adjacent twin. You can just see the twin vertices here. Because the neighborhood of any two yellow vertices will be always same, but they are adjacent twin. No matter adjacency or non-adjacency, the basis will remain the same. Therefore, we got another answer which is 12n, whereas their answer is 6n plus 1 to some 21n something. So this is exact answer when compared to the bound answer. And with all these answers, that is butterfly, fault tolerant multidimension of butterfly, fault tolerant multidimension of Bennett's network, and fault tolerant multidimension of this silicate network, along with the characterization result, we write a paper, and that paper was with us because we could not have confidence to write it to the journal. Then later we started inviting the eminent expert Sandy Glaser to see the paper first in the initial site, and we sent the other two papers, and somewhere there is an error, and all those errors we just pointed out and we gave the correct answers. And initially he said yes, you are right, and your answer could be improved. And later after his suggestion, the answer is rewritten like this: if U is a twin vertex of G and S is a fault tolerant resolving set of G, then U must be in S. That is the observation. Any twin vertex must belongs to a fault tolerant basis, and other than that, no vertex is required to form a fault tolerant basis. So with that, we will be able to get the lower bound. So if there is a graph, if there is a twin vertex, collect all twin vertex, put it in one basket, claim that as a fault tolerant basis. So that is going to be the lower bound. And upper bound cannot be disclosed because only twin vertices not possible to form a basis for some of the graph classes. For butterfly, the necessary, see this part is necessary part, right? This part is necessary part. Necessarily you need to have all twin vertices in the fault tolerant basis in order to claim this as a fault tolerant metric dimension or fault tolerant resolving set. But what about the sufficiency? Whether those vertices are sufficient to give or generate code for all other vertices of G, that is a question mark. And the characterization theorem in the mathematics paper was rewritten like here: let G be a connected graph, dimension dash is n, that is full vertex set, if and only if. The earlier paper it was given complete graph, whereas here it is a twin graph. When I say twin graph, each vertex of the graph must be a twin vertex. There are several graph classes. An example for that: complete bipartite graph, complete multi-parted graph are also an example of this twin class. So with this two characterization and the lower bound and the upper bound, we just case by case we prove for butterfly and Bennett's network. And we got the approval from Sandy, and with all his corrections and other thing, the paper got published in 2022. So this is our second essay paper. And after that, with that, we started working meticulously. We found several other networks, several other graph classes, several other papers with the same error, and all those errors are carried and corrected, and we write the paper. And now we can very well proudly say, with the help of twin our twin concept is effectively employed and generated with so many publications with few collaborative authors in our research centers. So this is the first paper in AMC, and this is again I would say after how many years of journey? 2010 I started, 2022 this paper came. After 12 years of journey only I got this AMC paper. And then later we got this another network in a computer science journal, that is engineering journal, where they introduced a new network with some definition, and the network goes like this. This is actually Engineering Science and Technology, an international journal, a Q1 journal elsewhere. Here, a new type hypercube variant called fractal cubic network was defined, introduced. So in that paper, the network is drawn here, for which the definition is given in the paper is misleading. Again, there is an error. We may say the period is a lucky period for us, because wherever we go, there are errors. So in the network you can very well see there are twins. Can you able to see? Look at here. These two vertices, this vertex and this vertex will have common neighbor, and these two vertex will have common neighbor. These two vertex will have common neighbor. Similarly, these two will have common neighbor. When you even extend, there will be twin presence. When you extend, again there is a twin presence. So what is the thing? Our duty is over. For this particular network, what is done? The hermetic dimension value is done, and lower bound is there, and of course this is bipartite graph. Definitely upper bound is also settled. So with 1 hour of time, we were able to get the lower bound, upper bound, the exact answer for this graph class. But only thing is, graph defined in this paper is wrong. Graph defined in this paper is wrong. See, with the wrong definition of this paper, when we write some answer and publish, later stage, this paper may be retracted. So when this paper gets retracted, our paper also will get affected. So what we must do, we should not take the wrong definition to paper and do the right content. Because our content is right. As per this network, the value of multi-dimension and fault tolerant multi-dimension is wrong, correct. But the definition of the network is wrong. So first job is to correct the network's definition and then investigate the problem on it and then get the answer. So in that aspect, we again started investigating, and we found where there is a mistake. I will tell you the mistake. The graph definition is like this. This is a redefined definition. In the original paper, the set E dash, the additional edge. See, every time when I increase the dimension number, when I increase the dimension number increases with the earlier existing graph with the 4 copies with the 4 additional edges. The 4 additional edges should be given in this E dash. Unfortunately, the authors gave all the connections in this E dash. So that is the only correction. You can just see here now. This is FCN0, and when you further move to the next dimension, I will have to take 4 copies of FCN, that is 4 copies of the earlier dimension, and I must have only this 4 connection. But in their definition, it gives all the 4 connecting edges. See, actually the graph drawn is this. We have redrawn this in the other way. The graph, what they suggest is this, with only 4 new edges from dimension to the next dimension. But in their definition, it gives this 4 edges, continued with this 4 edges, and this 4 edges, and this 4 edges. So together when I put, I will get this edge. This is the graph. So graph defined in this paper is this, but the graph drawn in the paper is different. So which means what? What has to be corrected now? Both can be corrected actually. Either you must correct the definition in order to get the earlier graph, or according to the definition, you must present this graph. But there is one more problem in this. You cannot present this graph because there is no twin. See, in the earlier case, there were twins, right? If I say this graph, there are twins. You can say this vertex will form a twin class. This vertex and this vertex will form a twin class. Okay, so graph drawn is correct. Therefore, we were able to identify the twin class, multi-dimension, fault tolerant, everything is immediate. But according to the definition, when I draw the graph, I get this graph class in which there is no twin class. And one more important thing, one more luckiest thing happened is this graph is isomorphic to hypercube. Which means what? The hypercube class is well established graph class for which you should not give new definition. So already it is in the literature. You have given some definition which resembles the hypercube which cannot be published. That is the thing, right? So what, where I will have to correct? I will have to correct in the definition, not on the graph part. So the definition was corrected in the later paper, and the new definition retains only these 4 edges and not the other 3 sets of 4 edges. So therefore, my part is comfortable because there exists a twin set. So twin must exist and definition should be corrected. The same graph class should be obtained. So many people, many situations helped me in constructing this thing. Suppose if that particular 4-edge graph, this 4-edge graph does not isomorphic to hypercube, then I will go in wrong end. So fortunately, this goes and end up with the hypercube isomorphism. Therefore, I can very well say, according to your definition, if you draw the graph, that will go isomorphic to the hypercube q power 4. Therefore, your validation is not correct. And I have given new definition, and with which we were able to generate graphs with respect to different dimensions. You can see there are 4 copies of the earlier dimension. The orange vertices are the link edges. Similarly, you can just generate, take 4 copies, give only 4 edges. Take 4 copies, give only 4 edges. And this network, this particular paper was again rewritten, and again we asked Sandy, there is one more correction. Would you like to join with us and then correcting the literature? He was very much appreciating our group, and he was enjoying the graph structure, the way we redrawn the thing and the other thing. And we immediately he joined, and he spent the first time he gave so many corrections. For this paper, he just gave only few corrections. With that, he approved the paper and we submitted to the same AMC journal. And you can see the twin sets here, and we got the answers here. And along with this, multi-dimension is not defined actually, because multi-dimension is a very old problem. The network is defined in the early stage. This particular problem is not investigated on that. Therefore, we started investigating multi-dimension together with the edge multi-dimension. At this stage, 2023, we were not aware of, or we were not strong enough to investigate the edge multi-dimension problem on this particular paper. So we just stopped with multi-dimension, edge multi-dimension, and correcting the definition of the literature. We successfully published this paper, second paper, in the next year, 2023. This is another happiest moment in publishing this paper. Then later, we started reading edgeometric basis and its fault tolerance. And here, the same concept, you need to take the subset of vertices. Only thing is, you will have to give distinct representation to edges instead of vertices. And for this particular thing, I just thought of one thing. If the vertices are getting the same representation with respect to all other vertices, definitely the connecting edges of that particular thing also will be the same. And I just requested my scholar to investigate on that. She started investigating. After a week of time, she gave approval. Yes sir, it is coming very well. With all the bipartite class, it gives the exact thing with this particular diagram. So this is the key content where U and V are twin. X is particular vertex in a neighbor, and you can just put all other vertices on the other side. So any vertex from that, if you want to travel, you will have to travel via X to the twin vertex U. So that travel must lead this particular edge receiving the same distance. See, this 2 vertex receives the same distance. Obviously, these 2 edges also will receive the same distance, right? So with that small spark, we started investigating another lower bound for edge multi-dimension using the same concept called twin sets. So that gave a nice result in this. This is what the next lower bound for the same set of graph class with respect to this. While investigating this, butterfly is not investigated, Venice is not investigated. Of course, the butterfly Venice has very rich literature, but edge multi-dimension is not investigated. And fractal cubic network was a recent introduced network for which also edge multi-dimension is not investigated. So we just took this lower bound, we applied, and we got these two results. This is the lower bound for arithmetic dimension, and this is the lower bound for fault tolerant arithmetic dimension. And finally, with the help of this, we just search the literature. Who are all the people who can able to contribute? This time we refuse Sandy and we go for geometric dimension, the introduction paper. In that is Ismail Hero from Spain. He has done a lot of work in geometric dimension, and he is Alexander Klein, and he also does many work in geometric dimension. We started writing to next collaborator. He is Sandy actually, the first paper inventor. We write mail to second collaborator from Spain, and he also immediately agreed. Yes, you are right. Your lower bounds are validated, and it will cover all graph classes of the particular same type, and we can very well communicate this particular paper. So that paper got communicated along with these results. Geometric dimension of the butterfly network. First fractal cubic network is 2 into 2 power r. Fault tolerant is 2 into 2 power r plus 1. Similarly, butterfly with the fault tolerant geometric dimension, and Venice with the geometric dimension and fault tolerant geometric dimension. Together with all the 6 results along with the lower bound, we were communicated the paper to Journal of Parallel Distributed Computing that got accepted recently and got published. So this is another milestone, but this came in the year 2025, but this we identified in the year 2023 itself. So from 3 we started writing, and the review process took long time, and finally it got published. And later we again we are not satisfied with the only 3 publications with particular twin concept. We were started searching for some other networks. While searching, we got this generalized Sierpinski, because the normal Sierpinski, again Sandy, our collaborator, has already solved the multi-dimensional problem for normal Sierpinski extension. So we just got this generalized Sierpinski graph with this definition, and the graph construction goes like this. Take any graph G, and how many vertices are there? There are 5 vertices. Take 5 copies of the same vertex set by prefixing the first vertex, second vertex, third vertex, fourth vertex, and fifth vertex as a bundle, and retain the edges of the same copies. So what you have done, you have just taken 5 copies of, that is whatever the cardinality of vertex set here, the number of copies you have to, and each copy you must prefix the letter. Say 1, here 2, here 3, here 4, and here 5. Some of the notions you will have start from 0 to n minus 1. So here I have taken 1 to 5, 1 to n. And the new connections are given in this way. The ultimate thing is, when you shrunk this portion, when you reduce that particular graph in one single vertex, similarly all the 5 copies with one single vertex, when you contract, you must be able to get this. So that is the extension of Sierpinski, and that we have given for generalized graph. So in this generalized graph, we started hunting for a new graph class but here there is no twin. Some small graph I have taken, I have given Sierpinski extension, whereas there is no twin. We started investigating whether there exists any graph with the twin in the base graph admits the same twins in the extension. So in that way, when we start, we got this another nice idea. He is Danny, and he is a US computer scientist. He was fond of constructing the architectures. While constructing the architecture, this connection machine, his PhD thesis was in the title of connection machines. His connection machine was like this. This famous hypercube actually. Here in this hypercube, there is no twins. So that we cannot employ our twin technique here in order to get the metric basis. Still now, the metric dimension of hypercube, geometric dimension, fault tolerant geometric dimension, any variance of metric dimension is not solved for hypercube. Of course, the problem is very old. Even the network is also very old, but the answer is not yet found. So we were not able to get the answer for this particular entire network, and we just compare the Sierpinski extension along with this. We got a nice structure with this. Now, what is the beauty in this too is, the vertex set of this is going to be the vertex set of this. Vertex set of this is going to be the vertex set of this. And only thing is, I have just removed some of the edges from here. Reducing edges from the interconnection network has a rich literature because the connection cost will get reduced. If you want to have more connections, you will have to connect with the wires. It will cost the interconnection network topology, right? You will require more cost to develop this particular network. I am able to construct the same processor with the less number of connections, and of course this graph is a spanning subgraph of this graph. So with this properties, we could able to find the twin classes here. This vertex and this vertex will form a twin. Only thing is, how when this particular extension goes, how many number of twin classes? Of course, each twin class will have two vertices. How many number of twin classes you will have? That is a very difficult thing, and that also solved. And finally, we got this as a spanning subgraph modeled like this graph. The next extension goes like this. Take 4 copies and join the edges, CA link edges, and get the network like this. Likewise, you take 4 copies, and finally you get the connections. In my luckiness is any extension, I am able to preserve my twin class here. So with the help of this twin existence, I am able to get the answer in a short span of time. Of course, the lower bound is also the upper bound. The necessary vertices are sufficient here. So with this, again we got another paper just with the Sierpinski and all our existing results. And later now we are investigating on the graph class where the necessity is not sufficient. In all the previous graph classes, the necessary vertices are sufficient, therefore we will be able to write a paper in a short span of time. Whereas here, the network PNN contains input layers here, hidden layers here, and output layer here. Whereas here again there is a twin class because these vertices will form a twin class, these vertices will form a twin class, all these input vertex will form a twin class. But here from twin class, if you are able to get the basis or arithmetic basis, the generated basis using the twin class may not be sufficient to resolve the graph. So this investigation is now communicated to Journal of Supercomputing. It is under review, and with famous graph operation like double graph, this gave a nice generalized results using the twin graph. See, double graph definition is like this. For any graph G, take the same copy of it. The additional links would be wherever a vertex is adjacent to a particular in the original graph, the image of the particular vertex will be joined. So here the edge would be from V2 to V1 dash because V2 and V1 are adjacent, V2 and V4 are adjacent, therefore V2 to V4 would be the new connection. Similarly, for other vertices, you will have to have a connection. The beauty in this is the graph what I have taken is a twin graph, right? The graph what I have taken is a twin graph because 2 pink vertices forms a twin class, 2 yellow vertices forms a twin graph. Once my operation is performed, the resulting graph is also twin graph. So general theory, if you take a twin graph, do a double operation, the resulting graph is also twin graph. So that twin graph, with immediately I can get the multi-dimension, immediately I can get all the 4 parameters discussed. So that is what this content. Look at here. Twin class again. This strong double graph, you need to have a self image also, including in the strong double graph and double graph, you will have a small change. Double graph you will have independent non-adjacent twin class. Strong double graph you will have adjacent twin class. Twin set you can see V1, V1 dash, V4, V4 dash together will form another twin set. V2, V3, V2 dash, V3 dash will form a twin set. So this is one beautiful result. The result is any twin graph you could take, do a double operation, you will end up with a twin graph, right? The another important thing is any twin free graph you could take, which means what? A graph with no twins. If you perform a double operation, the answer is again a twin graph. So that is another interesting thing. where you will have a twins of cardinality 2, because here each vertex is a single vertex, it will not have a twin relationship with any other vertex, right? So when you just to have a double operation, the vertex in the base graph, vertex in the new graph, together will form a twin. So whatever the graph cardinality you have, in the double graph you will have that many number of twin sets, each of cardinality 2. So that is going to be the another content. So with that you will be able to get the nice lower bound here. See here, first twin class I have given the bound, tk1, tk2, etc. tk are the twin classes of cardinal tk1, k etc. k are. In the double graph you will have these vertices are necessary, and of course they are all sufficient too. The next is twin free graph. When you have a G without any twins, then dimension of D of G is n, because every vertex of base graph and every vertex of the other image will form a twin set of cardinality 2, and of course I told all but one vertex of a twin set will form a basis. So in that sense, from two vertex, one vertex will contribute to basis. All vertices I can very well take it from the G itself. So the dimension of D of G is n, and of course the fault tolerant dimension is going to be 2n. And further we have this is strong double graph result. This is for Kn actually, complete graph with another complete graph. And see, when you do your strong operation with the Kn, you will end up with another complete graph for which already the results are available. When you have normal double operation, you will not end up with a complete graph. Therefore, it has to be investigated. That is what my current research. So, but now I am slowly moving on my particular twin concept to graph operation 2. That also gave nice results. These are my references. And thank you. Today we are celebrating St. Anne's Feast. So happy feast to all. Any questions?
Does anybody have any questions?
Now I kindly request Dr. S. Arumugham, eminent professor, to felicitate our chief guest, Dr. S. Prabhu, with a memento. Sir.
Now I request Dr. S. Arumugham, eminent professor, to please come onto the stage to felicitate Venugopal sir with a memento.
Thank you, sir. Now I call upon Dr. K. Nandita, Assistant Professor, to deliver the vote of thanks.
I took the privilege to extend our heartfelt gratitude to the one who written stories of insights in the language of numbers, to the one who have lit the paths for others to follow in the realm of research. As light needs no introduction, it's none other than Dr. S. Prabhu sir, a distinguished mathematician and a dedicated researcher. Sir, by sharing your invaluable contributions and inspiring insights about metric dimensions, you have shown us that mathematics is not just a subject, but a way of seeing the invisible structures behind the reality. Thus, mathematicians don't merely solve problems, they uncover the patterns that shape our world, and you stand as a great example for that today, sir. I once again thank Dr. S. Prabhu, who not only explores the abstract ideas, but brings clarity and curiosity to the society through his profound knowledge. Thank you, sir.
Thank you, ma'am. And I request all the participants to move to the dining hall for lunch. Please gather here at the same hall by 1:40 p.m. for another session. Thank you.
You can feel comfortable here.